हेलो एवरीवन. लाइव क्लास नहीं कर पाए, क्या क्या कैचअप कर लिया. दैट्स ग्रेट. एवरीबॉडी, hello everyone. Everybody can see me and hear me clearly. Happy Teachers Day. Thank you, thank you, thank you, thank you, thank you, thank you. Thank you so very much for making this day for me. Thank you everyone. Please share this session. Please share this session. Thank you, thank you. Lots and lots of love. Today is the last class. Okay. Thank you everyone. Thank you, very thank you. Today is the last class. Hopefully this class will last something around 4 to 5 hours, and in those 4 to 5 hours we are going to cover up our thermodynamics entirely. It will be over by today. Okay. Great. Thank you Shubham. Thank you, thank you, thank you. So today we are going to finish it at last, and meanwhile I want everybody to share the session, and since this is the last session of thermodynamics, and hopefully from tomorrow on we are going to start IC engines, which is a small topic, very small topic it is, and it only 3 cycles are given. Only 3 cycles are given. So we'll do, firstly we'll do that. Okay. And after that we'll see whether power plant, RAC, or some other HT, heat transfer, whatever subject that is going to start, we'll start. Oh, are you okay now, Sumit? Thank you, thank you, thank you. Menti कब है? Tuesday को रख लेंगे. We'll keep it on Tuesday so that you'll get 1 day to study the whole thermodynamics, and yeah, Menti will be on Tuesday. Okay. So let's just move forward and go through this. बता तो दिया सौरभ, बता तो दिया. Tuesday. Tuesday. Okay. Chalo, let's start. So today, no, you can take rest. You can watch it later on. No problem. We are going to start with properties of pure substances first. Properties of the pure substances. Let's deal with this, and let's see how the story develops. Thank you, Saurav. Thank you so much. Now, so in the very beginning of the class, please listen very carefully now. We are straight into the business now. Okay, so properties of pure substances. Today it's in the very first lecture itself, we got to know that what pure substance actually is. How do we define pure substance? So in order to define pure substance, the following definition is given. Which definition? See, pure substance is always a substance or a matter having homogeneous chemical composition. If there is a homogeneous chemical composition throughout its volume, it will be known as what? Pure substance. Is it clear? Now, the topics which will be covered in this are namely PV diagram. All right. Number 2, TS diagram. Number 3, PT diagram. Number 4, HS diagram. Means these are all graphs. Okay. So these are all graphs. Number 5, which is most important, properties calculations. All right. We'll do the properties calculations, and then some of the questions, miscellaneous, right? So let's start with what we know as PV diagram. Okay. I'll do it in a nutshell. I'll do it for you. What you people need to do is, you will get the notes available on my Telegram channel. And that Telegram channel is this. If you have not yet joined, you can join there. Over there, I'll provide the notes. Okay, after the class. Good afternoon, good afternoon, good afternoon. I'll provide the notes right after the class on that Telegram channel. So you need not write down anything. We are going to move forward. Okay. Difference between Keenan function and Gibbs function. See, the difference between Keenan function and Gibbs function is, Keenan function we are not going to study. Why? It is the part of chemical engineering. We are mainly concerned about Gibbs function, and today itself when we are going to derive Maxwell's equation, there you are going to see that Gibbs function, actually the Gibbs free energy concept is there of Gibbs function, right? So it tells about the feasibility of a process. You might have heard about it in your 12th standard, Gibbs free energy, negative Gibbs free energy, and so on, like that. Anyways, PV diagram. Number one, PV diagram. Please pay attention over here only. So this will be different for water and others. Suppose you have water and suppose you have others, right? Suppose you have water and then you have others. Others like you may have iron, you may have something else. But what happens with water is, see, peculiar nature of water. There's a peculiar nature of water. What is that? It is, this expands on freezing, and contracts on heating, which is opposite to the other nature. For example, you take a piece of block of iron. If you heat the iron, it will expand, right? If you cool it, it will contract. Simple is the case. Similarly goes there, but it is opposite. In water, what happens when you heat it, it contracts. When you cool it, it expands. Why is it so? We'll see. And because of this same peculiar nature, solid water, which is ice, what do you call solid water as? Ice. This solid water floats on liquid water. Yes or no? In general, whereas, like if I see here, see, whereas, if we talk about it, whereas, in other substances than water, in place of water, if we take other substances, right, solids sink in their respective liquids, right? For example, if you have liquid iron and you put some solid iron in that, it will sink, right? If you have, let us say, liquid aluminium, you put solid aluminium over it, it will sink. But in case of water, if there's a pool of water, liquid water, and you put some solid ice on it, it will float. Yes or no? And that was the reason for the, an iceberg. That was the reason for sinking of the Titanic, right? So this is the peculiar nature of water. This is the different, anokha. Peculiar means anokha, right? Different nature of water. So that, my dear students, is a peculiar nature of water. This is how water behaves differently than the other substances. Is it clear? Now you understand, please tell me. You have to be attentive today. See, I know we are going to stay together for quite a bit of time today. It won't be the same old usual class which you guys have. But in order to go and conduct long duration class, I need you guys to be interactive and attentive at the same time. So please tell me, now you understood that what is the real meaning of peculiar nature of water. So therefore, whenever you are going to see PV diagram, because of this peculiar nature, peculiar nature of water, its PV diagram is different अलग है from other substances. Is it clear? With respect to the other substances, its PV diagram is different altogether. You can take the screenshot if you want. Thank you, Sandeep. Good afternoon. Please take the screenshot. Okay? Understood now? In the next part, we'll see why peculiar nature of water. I mean, okay, we observe this. In our day-to-day lives, we observe this. For example, we want to drink some cold water and the cold water is not available. What can we do? We can take some liquid water, which is not so cold, and we can put some ice cubes in it. And meanwhile, you will see that the ice is floating. Yes or no? This happens all the time. But have you ever wondered why this happens to be very exact? Why peculiar nature of water? Today I'll explain it in such a way that your minds are going to, get blown away. Trust me. Right? So let's see why peculiar nature. So the reason for peculiar nature of water. Why the reason for peculiar nature? Why do we consider peculiar nature of water? There's a reason. See, what is PE stored in the bonds? Okay, PE stored in the bonds. That is potential energy stored when bonds form, right? Potential energy stored when the bonds are forming. Please pay attention. Yes or no? So how do we define potential energy? It is known as bond strength, is it not? Times bond length. All right? Bond strength times bond length. Okay? Bond strength times bond length. Please pay attention. Bond strength, bond length, potential energy stored in the bond. Okay? Actually, it is similar to force into displacement. See, there are two polar opposites. They are attracting each other, right? There are two polar opposite charges attracting each other. Now they must be applying some force, and that force is measurable in the terms of bond strength, and they are separated apart. That is bond length. So bond strength, bond length. That is the potential energy stored in the bond. Okay, that's how the potential energy in the bond is stored, my dear students. Great. Next, how do we define kinetic energy? Kinetic energy of a molecule. Isn't it proportional to its absolute temperature? Tell me, yaar. Or I should say that kinetic energy is 3/2 kBT. Or rather than doing this is only for gas. I can say this. Of course, higher the temperature, this is known by everybody. Higher the temperature, every dot will connect, don't worry. More shall be randomness. More shall be the randomness. Is it clear? The greater the temperature, the greater will be the value of randomness. Higher randomness will be there. Right? Okay. I did not write 3/2 kBT because that was for a gas, and now we are talking in general. All right. Now you tell me, if we have this energy parameter with temperature, this is energy. So I believe this will be potential energy. Yes or no? And from here you will have kinetic energy. Because as temperature increases, it increases linearly. Yes or no? It is increasing with respect to temperature. Of course, temperature will increase, random motion will increase, and when the random motion is increasing, definitely kinetic energy of the molecules is going to increase further on. Okay, everybody? So this is increasing. Now consider this zone. I can divide it into two zones. Please pay attention, this is very crucial. I can divide it into two distinct zones. What are these zones? Please consider. Please consider these zones. So what is happening in this zone? Kinetic energy, my dear students, is less than potential energy. What is happening over here? Kinetic energy is greater than potential energy. Am I right? This is zone 2. This is zone 1. Any doubts up till now? Any doubts up till now? Please tell me. No? Okay. Sir, how is this related to water? I'm just going to paint the entire picture in front of you. Please pay attention. Okay? Yeah, it's not break-even point. We should not say it break-even point. We should say that this point embarks zone 1. At this point embarks the separation of zone 1 from zone 2, or zone 2 from zone 1. Right? Okay? It looks like that, but it is not break-even point. Anyways, please pay attention. Please pay attention and have a beautiful look over this picture. This is a very, very, very beautiful picture, my dear students. How is it beautiful? Let me tell you the story. Now, if kinetic energy is greater than potential energy, bonds will break. Yes or no? Bonds will break. Is it clear? And if kinetic energy in turn is less than potential energy, then bonds won't break. Bonds won't break. They will not break. है ना? And they will stay in their positions. They will stay in their respective positions. They will not break. They will not change their positions. Is it clear? They will not do that. They will not do that. Okay? Simply, they will not, change their positions. The molecules will not move further apart, but in this case, the molecules will break apart. Is it clear? Understood? Up till now, understood? Now I'm going to tell you the entire story of water. So please pay attention and please take the screenshot. I request you guys to take the screenshot, please. Take the screenshot, everybody. I think you might have. Okay. Now, see. Hydrogen bonding in water. Water molecules. See, there is a peculiarity of water molecules, and why it is due to this hydrogen bonding. See, let me tell you. You have oxygen, there is a lone pair of oxygen, lone pair of electrons in the oxygen. The water molecules is H2O, right? Due to this lone pair, what happens? There is a partially negative charge on this, as well as there is a partially positive charge. Partially negative, partially positive charges will develop here and there. Yes or no? It's very simple. 12th standard chemistry, right? If there is a partial negative charge, polarization will occur. Partial positive charges will follow as well. Now you have yet another molecule, let us say. Yeah, H lone pairs. Now see again what is happening. See again over here, partial negative. You have partial positive, then you have partial positive, partial negative, right? Partial negative, partial positive. I mean the orientation is irrespective. We are not so much concerned about the orientation, but this happens, right? This happens. Now please pay attention everyone. Due to this, don't you think that these partially negative charges will attract the partially positive charges? There will be a bond. There will be a very weak bond although, but there will be a bond. Are you getting my point or not? These are known as hydrogen bonds, and so on. These will be known as hydrogen bonds. Now you can see. Okay? Hydrogen bonds. These are represented by this. Okay? Now due to the presence of hydrogen bonds, what is happening? Because of the presence of hydrogen bonds, since hydrogen bonds are present already, because of this presence of hydrogen bonds, what is happening? What in turn is happening? Please tell me. Because hydrogen bonds are present, because of that, potential energy stored in hydrogen bonds. We know this, bond strength times bond length. We have this, okay? Bond strength, bond length, we know this already. Now what will happen? Now what will happen? The potential energy stored in the bonds will be there, and when at low temperatures, kinetic energy is less, bonds can't break, bonds cannot break, we have already studied. So bonds cannot break because kinetic energy is less at low temperatures, which means molecules have a gap, more volume, less density. Less density. Opposite happens when here. Opposite happens, just opposite to this happens when at high temperatures kinetic energy more means bonds break, means no gap, means molecules come together. See what happens. See what is happening. See, there's a gap, okay, there's a gap, molecules are there, a bond is there, kinetic energy is less, that bond cannot be broken, means the bonds will exist, molecules are at a distance, they have a gap, bond length is there, but the moment kinetic energy is more, these bonds break. What happens? These bonds break. When these bonds are broken, now what happens? The bond gap is vanished and the molecules come together. When the molecules come together, simple. Understood everybody? Understood everybody? Yes or no? Means density is more. Less volume, more density. Now can you correlate the fact with water? Now can you correlate the fact of this with water? How? I am telling you once again. See, when you are increasing the temperature, density is decreasing. When you are decreasing the temperature, density is increasing. Yes or no? I mean, opposite I said. I'm sorry. When you have low temperature, you have, less density. Means ice. In ice, temperature is lower. And when the temperature is lower, bonds cannot be broken. Net-like structure. Hydrogen bonds. Got it, everybody? This is the best explanation possible. Please take the screenshot, then I'll move forward. Please take the screenshot, then I'll move forward. Please do it. Okay? Fantastic. That's great. Let's move further. Let's move further. See. Now, you know, ice floats on water because its density of ice is less than density of water, and this in turn is because of hydrogen bonds. Because what happens, see, let us say that we have minus 20 degrees Celsius ice. Then you go to 0 degrees Celsius ice. Then the bonds are broken, 0 degrees Celsius of liquid water. And then 0 degrees Celsius of liquid water. Then you move on to 100 degrees Celsius of water. Yes, this happens. Say yes or no. In general, this happens. But see, over here, 0 degrees Celsius, ice is there. Till ice is there, hydrogen bonds are present. Hydrogen bonds present. Start breaking. They starts to break. Okay. And when come at 4 degrees Celsius, all hydrogen bonds will be broken. Therefore, maximum density. Now you understood that the maximum density is corresponding to 4 degrees Celsius. Why? Because at that temperature we can consider each of the hydrogen bond to be broken and the molecules are closer apart. And when the molecules are closer apart, their volume is less, hence their density is more. Understood, everybody? Say yes or no. Great. Okay. This is very crucial, okay? Fantastic. Now we'll see, first of all, understood, everybody? First of all, we'll see PV diagram for water. First of all, we are going to see PV diagram for water in case of water. Now what happens when we see PV diagram for water? Let's take an example. You have minus 20 degrees Celsius of ice, and now you want to convert it into 120 degrees Celsius of steam, superheated steam. That you need to do. Now in order to do so, you will start heating, of course. What you'll do? You'll start heating. Okay, fine. Let's start heating it. So you have started to heat it up. So minus 20 to it will go 0. From 0 to it will remain at 0. Then at 100. Okay. Then it will move on to 100 only. And then it goes over to 120. So what is there? You have ice, super cooled ice. Then you have saturated ice. Then you have saturated liquid water or water. Then again you have saturated water, but this saturation is different than this saturation. And this is your saturated steam, and that, my dear students, is your superheated steam. Okay? Understood? So this saturated I am saying again and again. So what's the meaning of this saturation? We'll understand first. But meanwhile, let me give you the nomenclature. 1, 2, 3, 4, 5 and 6. Alright? You have these 1, 2, 3, 4, 5 and 6. Okay, let me just, after giving the nomenclature, let me just tell you what is saturation. See, this is known as saturated ice. Let me tell you, saturated ice. And saturated ice is solid. Yes or no? This is saturated liquid water. Saturated water, I should say. And this is your liquid. This, my dear students, is also saturated only. Saturated liquid only. Saturated liquid. Okay, saturated water, which is liquid. All right. And this is saturated steam. All right, this is saturated steam. Thank you, Sandeep, thank you. Saturated steam. Now, let me move on and let me give you the context. Okay, this is saturated ice solid, saturated liquid with respect to fusion. This one is with respect to fusion and that one is with respect to vaporization, and remaining is no problem because they have different names. Okay, so what is a saturation point? Saturation point during phase change. See, suppose you are preparing a sugar syrup, चाशनी. In Hindi it is known as चाशनी. हलवाई वाले के पास में होती है ना चाशनी और sugar syrup. So that sugar syrup is being prepared and that sugar is being added. So you keep on adding sugar. After some point of time, there is a point when no more sugar can be added, right? There's a point when no more sugar can be added. There comes a point. That point is known as saturation point. In the same way, over here, what are you doing? You are increasing the temperatures. What are you doing? You are increasing the temperatures. So, if you increase the temperature of the phase which is solid, there will come a point when if you further supply heat or if you further try to increase the temperature, it won't increase. First, all the bonds will be broken and this entire solid will be converted to liquid. That point is saturated solid point. Understood? In the same way, you keep on increasing, you have changed the phase. Now, this is saturated liquid. Why? Because it has been just obtained from this, and if you want to cool it, you will get solid. So beyond this point, you have different phases. At this point, you have water, and beyond this, water, and after this, what do you have? Before this, what do you have? Ice or solid, right? This is saturated liquid again. Why? Because from liquid you are going into steam. So saturated liquid. But there is a difference, let me tell you. There is a difference. This saturated liquid is with respect to fusion. It means if you go like this, if you go opposite, if you cool it now, you'll get solid, which is known as fusion process. And if you go beyond this, you will undergo vaporization. It will undergo vaporization. Simply, it will undergo the process of vaporization. Khatam. Now you understood saturation. Point beyond which, point or a state beyond which only there is a change in phase. There is a change of phase and not, there's a change of phase and not, there's a change of phase. Change of phase. Beyond this, change of phase. Got it now? Got it now? हाँ, ये भी ठीक है. रंग रूप बदल जाता है. Understood? Please take the screenshot, my dear students. Please take the screenshot and then we'll move forward. And then we'll move forward. Is it done? Okay. Shall we move forward? Tell me. Now don't you think this all heating is occurring at constant pressure, let us say 1 atm. This entire heating is occurring at 1 atm. Okay, this entire heating is occurring at 1 atm. Take another screenshot so that it will be fine with you. Entire heating is occurring at 1 atm. Thank you. Let's move forward. Okay. Now, so if we plot on PV diagram, what are we going to get? We are starting it from the scratch. You understanding? We have started it from the scratch. Abhi tak we didn't know anything. Now we know something. And after completion of this topic, we'll know everything. Are you getting it? So don't worry about it. You have a doubt. What is your doubt? Please ask. Okay. It will occur at constant pressure. So now here you have 1 and then you have 2. But, there's a but. What is that? At 2, volume is maximum, but at 3, the volume is decreasing, I told you. And density is maximum at 4. Say yes or no. And up till 100 degrees Celsius, which is 4, it is liquid only, and in liquid ice floats. So what I think is that 3 and 4 will lie here. Say yes or no. Say yes or no. Say yes or no. Understood? After that, you have point number 5 and then you have point number 6. In your peak and arc, when you'll see this in your diagrams. What's the meaning of this? That the latent heat of vaporization is more. Right? The latent heat of vaporization is more. Are you late, Preetham? Are you late? If you are late, then please watch it again. If you are not, then I'll explain. See, what did I tell? That at this point, there's a change of phase. Alright? This is happening at constant pressure. I am representing it on PV diagram. So this is 1 atm. 1 atm. Now what happens? 1 point is subcooled ice or supercooled ice. 2 is saturated ice. But from ice to water, density increases. Density of water is more. Density of water is more, which means that its volume will be less. So water, 3 and 4, at 3 and 4 points, we have water. We have water. Density will be, density is more means volume is less, because density equals mass per unit volume. So for the given mass, if you have higher volume, less density, more density, less volume. Khatam. Is it clear, everyone? And so on. Further, you can also draw it for, let us say, 2 atm. How? 1 dash, 3 dash, 4 dash, 2 dash, 5 dash, 6 dash, and so on. Understood, everybody? Say yes or no. Say yes or no. We can keep on drawing. Okay? We can keep on drawing. Now, points. I am giving you a simple trick to remember. Otherwise, you'll keep on cramming. You'll keep on mugging things up and it will be always difficult for you. Right? It will be always difficult for you. You'll keep on forgetting as well. So let me give you the key points. Let me give you the key points. Number 1. 2, 3, 4 and 5. There are 5. These are all what? 2, 3, 4, 5. These are all what? Saturation points. Am I right? These are all what? Saturation points. These are all what? Saturation points. Okay? And at 2, we have saturated liquid. Alright? At this, we have, saturated solid. Wasn't it? We had saturated liquid. Yes or no? This is saturated liquid again. But this was with respect to fusion, and that was with respect to vaporization. Understood? This is saturated vapor. Am I clear, bachcho? Yes or no? Am I clear? Saturated vapor. 3 and 4 I have doubt. 4 density is maximum. Will not that be swept? 1 ATM case. Baba, you tell me. I'm not saying this 4 is 4 degrees Celsius. This 4 is 100 degrees Celsius. And when I am saying that it has maximum density, means beyond this density is less. Beyond this density is less. Getting it? Density is less. But it is not lesser than ice. So which means that this point will lie beyond 2 na? Whether be it 1 ATM, 2 ATM, 3 ATM, 10 ATM, whatever. Yes or no? Got it, everybody? That is a state 4. That's why I have written points. Joining these points for different pressures will give, if I join these points for different pressures, will give lines. Yes or no? Means 3, 3 dash, 3 double dash and so on will give me saturated solid line. You understood, bacha? This is how I teach and this is how I make things easy. Earlier, this is drawn. Oh my God, this is something, and suddenly there is something else, and there you have. You will be confused. You will be confused as anything, right? But let's just understand that what saturated lines are. They are a combination of saturated points. That's all. Isn't it? 4, 4 dash, 3 double dash. Saturated 2 hoga na. 2, 2, 2. 3, 3 dash. And so on. Saturated liquid line with respect to fusion. 4, 4 dash and so on will give us saturated liquid line once again, because these are saturated points only. Saturated liquid line with respect to, again, vaporization. Vaporization. Am I clear? Great. And then you have phi, phi dash, phi double dash, so on. And this is your saturated vapor line. All right? Isn't it simple enough? Tell me, isn't it simple enough? Isn't it simple enough? Please tell me. Yes? Boom. You have this. Right? Now no need to rectification. No need to rectify this. No need to do that. We'll draw the graph. Now let's draw the final graph. So let me tell you, let me give you the context once again. So various processes were drawn, various heating processes were done for different pressures, and correspondingly these points were joined. and there was some sort of a diagram which came out, and that diagram which came into existence is something which we are going to study now. Okay, so please do it. Please take the screenshot, then we'll move forward. Please take the screenshot, my dear students, then we'll move forward. Okay, fantabulous. Let me just move forward. Okay, so please don't forget, this is our PV diagram for water. This one I am drawing for water. See, PV diagram. Okay, PV diagram. Now see. So, what is this actually? What is this actually? What have we got here? Right? Let us see. Bachon, let me come back here. I am saying this is SSL, saturated solid line, SSL. This is SLLF, saturated solid liquid line with respect to fusion. SLLV, this is SLV, saturated vapor line, SVL, sorry. Okay, so when we are drawing that which we have drawn, we don't need to write the whole phrase as together. So we don't need to write the whole phrase. Okay, let's do it then. What is this, my dear students? This we have drawn by joining 2 points. So this is saturated. This is what? Saturated solid line, isn't it? This one we have drawn by joining saturated liquid with respect to fusion. SSLF. This is SLLV, vaporization. This one is saturated vapor line. Finish. Got it? This point, my dear students, is known as critical point. I'll tell you what critical point is, but before that, please pay attention. Understood? And this, my dear students, is known as triple point line. Triple point line. Okay. Now rest of them are observations. But have you got the context? Have you got the idea? The saturated liquid line with respect to fusion, saturated solid line, saturated liquid line with respect to it, and then further when we move forward, it is observed to be going like this. Okay, it's an observation. Understood? Understood, yes or no? Is it clear? Please tell me. Is it clear? Fine. So you'll have the observations. Let me tell you. Over here you have solid. Over here, what do you have? You have solid. Here you have liquid plus vapor. Here you have vapor. And then in this is between liquid line, you have liquid plus solid. And there you have solid plus vapor. It means that below this triple point is a line. Yes, triple point is a line. So observations. The very first observation is, before drawing the observation conclusion, over here, over to this side, let me draw PV diagram for substances other than water. Understood? Substances other than water. Okay? PV diagram for the substances which are other than water. So if we see this, then only we'll be able to compare. And do you know it will be drawn similarly? See. You have PV here, and then you have, that is the difference. Solid, solid plus liquid, liquid, liquid plus vapor, vapor, solid plus vapor. So there is no overlapping. So there is no overlapping. When you are going from, let us say, subcooled or supercooled solid, you will go to, this is saturated solid line. This is saturated liquid line with respect to fusion. This is saturated liquid line with respect to vaporization. This is saturated vapor line. And that, my dear students, is your critical point. Understood, everyone? And this, my dear students, is your, again, triple point line. Understood? Yes or no? Got it? Understood, everybody? There's a difference. In this, there is an overlapping. See, saturated liquid and saturated solid lines are overlapping. Why? The density is more. In this, there is no such case. Simple. Okay. Now you can go with the observations. Now you can go with the observations. Number one, in both, for water and substances other than water, triple point state is a line on PV diagram. What is triple point state? It is a line on PV diagram. Okay? It is a line on PV diagram. क्या है ये? यहाँ देखो, ये वाला है ना, इससे पीछे चला गया. 3 point you are getting 3 point below this. Your network is causing troubles. Because of that, everyone will suffer now. See, so if you draw this, you will get saturated liquid line here, like this. Saturated solid line, sorry. This is saturated liquid line, and this is saturated liquid line. So that is differing. This is there. क्या है ये? यही है. All right, everybody. Understood? Say yes or no. Understood? Say yes or no. Please tell me. Please take the screenshot. Please take the screenshot. Everyone understanding? Everyone understood? Tell me. Okay. Now, in thermodynamics, number 2, observation, it is common observation. For both, critical point. Let me define critical point. It is the point at which, it is simply a point at which both saturated liquid line with respect to vaporization and saturated vapor lines intersect or meet each other. Okay? Yes or no? the saturated liquid line, see. And number 3, then I'll be able to give you more context. In thermodynamics, only liquid to vapor and vapor to liquid conversions are important. Only these are important. Therefore, liquid to vapor and vapor to liquid. Therefore, we take only this into consideration. Please see PV diagram. Okay, liquid vapor, and then vapor. This, my dear students, is critical point. This is saturated liquid line with respect to vaporization. That one, my dear students, is your saturated vapor line and critical point. Okay, that is critical point, liquid plus vapor. Understood, yaar? It's so damn simple. Now, therefore, in thermodynamics, you must have heard about it. Okay, you tell me, beyond this we have liquid, beyond that we have vapor, and above critical point we only have gases. But at critical point, phase is not defined, not at. See what I am saying? At this point you cannot define the phase. Why? Because you have saturated liquid line, you have saturated vapor line. They both are coming and intersecting with each other. When both of them are coming and intersecting with each other, then you cannot tell, you cannot be sure as to what the exact phase is. Because liquid is also there, vapor is also there. So what exactly is the phase? You cannot tell by simply at critical point. But yeah, above critical point you have only vapor. Only gaseous phase is there. And below you have some conversion. But above you only have gas. Got it, everybody? Understood? And also see for yourself. If you check this out, what do you have here? Pressure 1, pressure 2, pressure 3, pressure 4, right? So at higher pressures, what does this line indicate? Enthalpy of vaporization. Enthalpy of vaporization decreases. Why? Because why does it happen? Because the difference between two phases starts decreasing. See, you have liquid, you have vapor. Here there is more gap, here less. At this point, at critical point, there is no distinguishing between whether you have liquid or vapor. Means at this point phase is not defined. So when we are moving up, this will decrease. At higher pressures, enthalpy of vaporization will decrease. Latent heat of vaporization. Got it? Yeah, enthalpy of vaporization means actually latent heat of vaporization. That is enthalpy of vaporization. Got it, everyone? Say yes or no. And last but not the least, there is your PV diagram. See, let me tell you this, my dear students. Let me tell you this. Can you see now? dV in liquid, and this is dV in gases, and this is dP in both, same dP. Means for the same change in pressure, that is dP. For the same change of dP, you have dVL much less than dVg, because liquids are, बोलता रहता हूं ना मैं बार बार, I always keep on saying liquids are incompressible. Yes or no? So no matter how much pressure you change, the change in volume is very, very, very small with respect to change in volume of the gas. Got it, everybody? So this is all about your PV diagram. Understood? 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 Good afternoon, Akash. Good afternoon. Good afternoon. Very good afternoon. Is it clear, everybody? Is it clear? Please tell me. Please take the screenshot. मजा आया? मजा आया? Understood? So see, this is how we get this result. Right? This is how we get this result. And this is why it is very, very, very important. Okay, everyone? This is why it is very, very, very important as well. So shall we move forward? Shall we move forward? Okay? Fantabulous. Now let's move on to the other one, TS diagram. There is no issue in TS diagram. Let me tell you, TS diagram is very simple, same for both water and others. It is same for water and others. Why? Because on abscissa, on coordinate systems, we don't have volume. Yes or no? Since there was volume was there, therefore the nature changed, the graph changed, everything changed altogether, right? But since there is no volume on any of the axes, you simply don't need to look for different curves. You have only a single curve, right? Let's see. So now again same example. What example did we have? Remember 20 degrees Celsius minus 20 degrees Celsius ice was subjected to 0 degrees Celsius ice. Again 0 degrees Celsius water, 100 degrees Celsius water, jal, pani, neer, Varun, water, steam, गुस्से वाला Varun, and then 120 degrees Celsius, superheated steam. Got it? That was your 1, 2, 3, 4, 5, 6. You remember this example, no? All right. What was it? Saturated solid. Saturated liquid with respect to fusion. Saturated liquid with respect to vaporization. Saturated vapor. You remember, no? Bas, that's it. Now it becomes very simple. Heating occurs at constant pressures? Yes or no? Various pressures are there. It is P1, P2, P3, P4. I mean constant pressures. It occurs at constant pressures. That is very important. Okay. Let's just move further. Now, if heating is occurring at constant pressures, you have TdS equals dH minus VdP. Now is dP 0? Yes, dP is 0. Change in pressure is 0. You have TdS, that is Cp dt. Now what do you have? TdS equals Cp dt over T. Yes or no? You have Cp dt over T. Now you have ds equals to Cp dt over T, or delta S I can write Cp ln T final over T initial. I can write this? Yes or no? Means variation of entropy with respect to temperature is logarithmic. Number one. Yes or no? I will vaporize. Yeah, some Thanos will come and I'll vaporize. That's great. Logarithmic. Huh? Variation of entropy with respect to temperature will be logarithmic. That is logarithmic. Got it? Okay. Now please pay attention. This is very important. This is ultra pro important. During phase change, during sensible heating, temperature increases, entropy increases. And during phase change or during latent heat, what happens? Temperature is constant, but entropy increases. How? Delta S is given as latent heat upon saturation temperature. Say yes or no. Concept is clear or not? Please don't have a single piece of doubt in your head that, sir, during latent heating or phase change, we don't have like temperature change, temperature is constant. Then is entropy not changing according to this formula? Entropy will change. But how will it change? It will simply be given by latent heat upon T saturation, because it is occurring at constant temperature. Understood, everybody? Say yes or no. Take the screenshot, please. Take the screenshot, then we'll move forward. Please take the screenshot. Everybody. Please take the screenshot, everyone. Shall we? Oh God. Oh my God. Shall we? Great. Today again, due to some traveling or something, आज भी हालत ख़राब हो गई है, बट ठीक है, कोई नहीं. हो, shall we start? How long? अरे जब तक टॉपिक ख़त्म नहीं हो जाता. शॉर्ट में भगाना है क्या? You want me to skip some concepts? Do you want me to do that? No, na? So please pay attention. Yeah. What is it? What was I telling you? Okay. Now please see. Let's draw a sample. TS diagram. So in the beginning you have 1. So 1 to 2 is logarithmic because temperature is changing, minus 20 to 0, and then phase will change. Okay, phase change occurs. 3. Then again temperature change. 4. Then again phase change. 5. And then again 6. Okay, yes or no? You remember this? Concept is clear. So this is, let us say, at P1. You can draw the similar diagram at P2. 4 dash 3 dash 2 dash 1 dash. All right, so you have this. Okay bachcho, okay. Now upon joining all the respective points for various lines, I mean for various saturation points, what do you have here? TS diagram is obtained. All right, so we can obtain TS diagram. Now see, so how do we see our TS diagram to be as? Have a look. Like this. This is how we obtain our TS diagram. Okay, this one is saturated solid line, saturated liquid line with respect to fusion, saturated vapor line, saturated liquid line with respect to vaporization, saturated vapor line, critical point. And what is this? Triple point line. What do you have here? Solid, solid plus liquid, liquid, liquid plus vapor, vapor, solid plus vapor. Here also triple point is a line. Okay. Critical point is a point at which two things are happening. What? Saturated liquid line with respect to vaporization and saturated vapor line are intersecting. Yes or no? And apart from that, and phase is not defined. Right? Phase is not defined at critical point. Okay, above critical point, we only have, I have already told you, we only have gases. Okay, is it clear? Is it clear, everybody? Say yes or no. Is it clear, everybody? Concept is clear. Shall we move forward? Now, one more observation. Please pay attention. Difference between the vapor dome. What is vapor dome? Liquid vapor region. This is vapor dome of PV and TS. You will say, sir, similar diagram is being formed, but there is a difference. Is that vapor dome is broader for TS and narrower for PV. Why? Why is it so? Because I told you, you have incompressible, compressible. Combination is there. You remember? But in this, there is no such case. That's why it is open. And in that, it was like this. Fissile patti. Okay? Understood? Please take the screenshot. Please take the screenshot. This is your TS diagram. Understood now? Whew. Understood, everybody? Understood, everybody? Shall we move forward? Okay. Let's move forward, guys, and deal with the question itself. हालत खराब है आज. देखिए, understand the note point. Understand the note point. See, in this diagram, are you getting a temperature below which solid will directly convert into vapor? Because below this temperature, solid will directly convert into vapor. And in PV diagram, you are getting a pressure below which the solid will directly convert into vapor. Yes or no? So, triple point, pressure and temperature are those states below which solid can be directly converted to vapor. All right, you can directly convert solid into vapor. Please remember this. This is ultra important. Okay. So from there you are getting the pressure and temperature below which your solid is directly converting into vapor. Understood, everyone? Understood, everyone? This is very exciting. I hope it is clear to you. Okay. So these are the characteristics of that. These are simply the characteristics of that. All right. No problem. Nothing. Let's move forward. Okay. Now, triple point is a point on PT diagram. Yes, and that's what we are going to study next. Now we have pressure versus temperature diagram, or we should call it PT diagram. PT diagram. Now the basic concept behind PT diagram, the basic and core concept behind PT diagram, please pay attention. Please pay attention. The basic, very basic concept behind PT diagram. What happens is, see, very important. Phase change occurs at constant pressure and temperature constant. Yes or no? Yes or no? At constant pressure and constant temperature, phase change occurs. Tell me. Therefore, on PV and TS, we had two phase regions. But here we won't. देखो, मैं क्या कहना चाह रहा हूं समझो. What am I saying? This is a two-phase region. This is a two-phase region. That is a two-phase region. Why? Because the change of phase occurs at constant pressure and temperature. But, for example, if I do pressure here and temperature here, PT diagram, so phase change occurs. For example, you are saying, sir, this is the pressure, 100, phase change is occurring, this is 1 atm pressure, right? And you have 100 degrees Celsius. But what if you change the axis? Pressure this axis, temperature this axis. So, pressure 1 atm, temperature 100 degrees Celsius. Are baat khatam? You will get point. Yani you will not get what? A two-phase region. You won't get this line. You will get a point. Understood? This is very crucial. This one is very crucial, my dear students. Got it? You won't get a point, you won't get a line, rather you will get a point. Okay? Rather you will get a point. Understood, everyone? Is it clear? Is it clear? And this is very important. How? Means phase change does not occur along a line, but it occurs at a point. All right? It occurs at a point, not along a line. It will always occur at a point, never along a line. Never. Understood? Understood? Okay. You have different PT diagrams for different, you will see different PT diagram. Okay, pressure and temperature diagrams will be different for water and others. Water and others. I'll tell you each and everything. First, let me draw the diagram. See for yourself. Okay, so this is for water, substances other than water. Now what is the difference? Visibly it doesn't feel like any difference. Okay, हाँ तबीयत सही है भी नहीं. Let's have a look. Okay, this is our saturated or vaporization curve. If you pay attention, I am not writing saturated this line, saturated that line, because saturated lines were significant in PV and TS diagrams. But over here, we don't have those lines. We'll have only points. And those points are lying on this. Means this is the line which we are getting by drawing the points, joining the points, and this tells us the entire vaporization curve. Means beyond this vaporization will occur. Simple. There is also a vaporization curve only. Okay. What is it? It is a fusion curve. Fusion curve. Similarly, what is this? Simply nothing but fusion curve. And what is it? Sublimation curve. This is also what? Sublimation curve only. And what this point is, now you will be understanding. This point, my dear students, is triple point. Triple point. See why? Because below triple point, sublimation occurs. Yes or no? Below triple point, sublimation occurs. You understood why you are getting this? You are not getting two-phase regions. Why you are getting these? Why you are not getting two-phase regions? What's the logic behind getting these curves, not regions? Because phase change occurs at constant pressure and temperature, and on abscissa and ordinate you have pressure and temperature only. Okay? You have pressure and temperature only. Is it clear? Is it clear, everybody? Say yes or no. Is it clear, everybody? Shall we move forward? Okay, no problem. Triple point, triple point. Yeah, triple point. T point, triple point. You'll understand. Now, see, if I talk about it, see the slope. Slope of fusion curve is positive. Over here, the slope of fusion curve is negative. Do you have a positive? No. You'll see you have a negative slope. You have a positive slope. Is it clear? Although the slopes are very less. I mean, the slopes are, this is the slope. Infinite slopes are there. Large slopes. There is no change. But here is more change. Why? Why there is more change? Why the slope is less? Why the slope is more? You getting my point? And also, triple point is a point. Triple point is a point. So on PV and TS diagrams, triple point is a line. On PT diagram, it is a point. Got it, everybody? Please tell me yes or no. Copy it down, please. Or take the screenshot. Take the screenshot. Please take the screenshot. Shall we move forward? Clear? All right. Let's move forward. Let's move forward. Done. Now, since that is an observation, the slope of that, let me give you one another context. DTS and DTG. DTV you can say. No, DTS and DTG for the same DP. So DTS is negligible is very much less than DTG because solids are incompressible. Means boiling point temperature varies significantly with respect to pressure. And I have given it to you with an explanation in the classroom. I have given it to you with the help of an explanation in the classroom itself. Right? I have given you an example. Right? We had one notebook and I was blowing air into the pages of that notebook. So those pages were flapping. Right? And if I were to put a paperweight on that, then they will not separate so readily. Yes or no? That's what we are getting. So for melting point temperature does not vary with respect to pressure, we can say, but boiling point temperature varies with respect to this. Assertion reason question can be asked. Got it? Boiling point temperature varies with respect to pressure, but melting point temperature does not vary with respect to pressure. Understood? Got it? It's very simple. It's very simple. Now that, my dear students, is your PT diagram. PT diagram, TS diagram, PV diagram we have done. Is there any doubt? Please ask right away. Is there any doubt? Please ask right away. No? Now there is one HS diagram or Mollier chart. Okay. You have number 4. HS diagram. I'll make it very simpler. Very simple. Or Mollier chart. Let me give it to you in a context that you will understand. So, same example. 1 to 6. That is same example. How? -20, 0, 0, 100, 100, 120. 1, 2, 3, 4, 5, 6. Alright? This all is occurring. This is saturated solid. I have already told you this. Liquid with respect to fusion. Saturated vapor with respect to saturated liquid with respect to vaporization. And saturated vapor. Alright? I have already told you all this. No need to drag this example again and again in the same way. Okay. Don't you think that this entire heating is at constant pressure condition? Yes or no? This entire heating process is occurring with respect to constant pressure. Say yes or no. This entire heating is at constant pressure process. Yes or no? This entire heating process is occurring with respect to constant pressure. Is there any doubt in this? Is there any doubt in this? There should not be. There should not be. Okay? There should not be. Fantastic. Which means that TDS equals dH minus VdP, constant pressure, means dH equals TDS. I can say this, means dH by ds, constant pressure is T. What is it? It is the slope of an isobar on HS diagram. Okay, you have HS diagram and that is the slope. And what is it? Equals to absolute temperature. Now this relation will fetch you an immense understanding. Because of this relation only, entire HS diagram will become a piece of cake. Please do this, then we'll move forward. Please do this, then we'll move forward. Chaliye. Shall we? Okay. Wait. Let's see. Let's see. Now, because dt over dH over ds is T, means as heating is done, as we do heating, temperature increases, means that you have increasing slope. Increasing slope. Alright, that you have increasing slope. During latent heat, latent heating, you have constant temperature, means constant slope. Understood here? If temperature is constant, which is equal to the slope, slope will be constant. If temperature is increasing, then of course that too is increasing. Means what? Let us just apply this to HS diagram. What is happening is from 1 to 2, and then 2 to 3, 3 to 4, 4 to 5, and then 5 to 6. What is happening? Please pay attention. Temperature is increasing, hence increasing slope. Between this 2 to 3, constant slope. In this increasing. In this constant. In this increasing once again. Okay. Understood? Yes or no? Because between 4 to 5, phase is changing. Got it? So don't you think this is similar to trick? Let me give you the trick. Similar to TS but slightly rotated. See, if I drew this, it will look like this. Now TS was like this. I'm just doing this. Simple. It means that HS will be, see for yourself. Solid, solid liquid, liquid, liquid vapor, vapor, solid, vapor. Understood now? Why I am doing this? Why have I done this? Please tell me. See, now you will understand. Now you will understand. Six dash, 5 dash, 4 dash, 3 dash, 2 dash, 1 dash. Yes? So it is similar to TS diagram. TS diagram, on TS diagram, what we draw, it is similar. It just skewed, or we should say it is just rotated. So that's what we are getting. Simple. And again, triple point is a line on the HS diagram. Okay? Now, only this vapor dome is important to us. Critical point. All right. See, in liquid plus vapor region, means vapor dome, constant pressure lines are inclined and not horizontal. Why? Because if they become horizontal, then the slope is 0, and slope t cannot be 0. T is not 0. When t is 0, capital Z, T is 0, then only they will be. But it is not, so it is inclined. Got it? Number 2. In vapor region, constant pressure lines are diverging, and in wet region or vapor dome, they are parallel. They are parallel to each other. Got it? In that region they are diverging. So they are of diverging nature, and over here they are parallel to each other. Got it, everybody? Say yes or no. Please take the screenshot. Please take the screenshot, everyone. Okay, shall we? Now, you have this. HS diagram is done. I don't think so there will be any problem. I don't think so there is going to be any problem till now. Clear? Clear? Okay. Let's deal with a new topic known as dryness fraction. And this topic, my dear students, is ultra important from your examination point of view, because many questions are asked based on this. Many questions are asked based on this dryness fraction only. So how is dryness fraction understood? What is dryness fraction? How do we consider dryness fraction? That is something which we are putting our focus to. Now let me tell you. For the graphs with two phase regions, means except PT, yes or no? We are concerned about the graphs except PT. PT diagram, you don't have two phase regions, you just have curves. Yes or no? You don't have two phase regions, you just have curves. That's what you have. Now, let's say, for example, TS. For example, let's go with TS diagram. You have this, okay? This is saturated liquid line, I can say SLL. This is saturated vapor line, SVL. Means over here we have saturated liquid. On this line we have, saturated liquid only. And over here on this line is what we have, saturated vapor only. Okay? Saturated liquid only, saturated vapor only. That's all is there. Saturated liquid, saturated vapor. Okay? Shall we move forward? Shall we move forward? Saturated liquid, saturated vapor. Now, please pay attention. Saturated liquid, saturated vapor. Now I need to find out dryness fraction. See, at saturated liquid line, only liquid and no vapor. Yes or no? Whereas at saturated vapor line, you only have vapor and no liquid. Right? But in the vapor dome, like if we talk about what is happening in the vapor dome, what should we do? Inside this vapor dome, mixture is composed of liquids and vapors. Right? We have mixture which is composed of liquid and vapor both. So you have the mixture which is composed of liquid and vapor both. Now what happens? Now what happens? Please pay attention. Please pay attention. M equals to ml plus mg. This we know. Now dryness fraction X is defined as the ratio of the ratio of mass of, see it is dryness, so mass of vapor present in the mixture with respect to mass of the gas, mass of the liquid present. Okay, see, mass of vapor present upon total mass of the mixture present, my mistake, mass of the mixture, total mass of the mixture, that is liquid plus vapor, both liquid and vapor both. Understood? Liquid and vapor both. Please try and understand. Please try and understand what I am trying to say. See, if this is the vapor dome and let's say phase change is occurring, there's a change of phase. I'll give you a break. Okay, don't run like you are running away and doing this and that. Don't run away. You'll be getting a break of 20 or 25 minutes or so once we complete this chapter. Because after this chapter there is yet another chapter of 1 or 1.5 hours. Okay, so we'll take a break between that, then we'll continue. And this chapter is about to be completed in a few moments of time. I mean in half hour or 45 minutes. We'll do a few questions as well before going. Got it? Got it? So now, defining it as a ratio of mass of vapor present in the mass of mixture with respect to that. Now what is happening? See, in this pressure is constant as well as temperature is constant. Now if somebody asks you that okay, phase is changing, tell me at which position it is lying, at which position you have the state, where would you mark 1? Where would you mark? So there must be something else which should be given in general, because here it is entropy. If I do PV, I'll have over this axis as V. So that cannot be this. I mean, only entropy and volume are not, I mean, they are specific, they are very precise, so that if entropy is given, that would be given only for this. If volume is given, that would be given only for PV diagram. But right now we are interested in this in general. By which point, by which property or by which term can we define the position of state in two-phase region? Okay, so what does it do? It tells about the location of it tells about the location of the state, okay, in the vapor dome during phase change. Okay, this is the purpose. Many a times in interviews it is asked that why are we giving this? What is the reason for giving this? Why are we studying this? Why dryness fraction is studied at all? So the main reason for studying dryness fraction, my dear students, is because we want to locate the position, locate the state, locate the exact location, mark the exact location of state during phase change. Okay, as to where at that point of time it is lying. Which means that x equals what? Mg over m, or I should rather say mg over ml plus mg, which means that the value of x lies in the close range of 0 and 1. X equals to 0 at saturated liquid line, x equals to 1 at saturated vapor line. Simple. Understood now? Understood now, everyone? Please tell me yes or no. Is it understood? Please tell me. Take the screenshot, everyone, please. Take the screenshot, everyone, please. Is it done? Okay. Great. I hope it is understood. Now we'll move forward. Okay. Saturated liquid, saturated vapor. Now see. X. Okay. Also, at critical point, at this Cp, critical point, is it divide or minus? Where is it divide or minus? It is divide. Where are you saying? It is divide, yeah. Is divisible by, is equal to. What is mass? Mixture, mass of the mixture. Mixture contains liquid and gas, no? So that is not minus, yeah. That is equal to sign. Anyways. So at critical point, no phase is defined in particular. Alright. There is no definition of phase. Phase isn't defined. Right? Phase is not defined at all. And because the phase is not defined, you cannot define the phase at critical point. All the constant dryness fraction lines start from critical point and run parallel to their respective saturation curves. Now what does it want to say? What does it want to say? Let's have a look. What does it want to say? Let's have a look. It is saying that, let us say it is TS diagram, right? And this is a critical point. So all of those are starting from here. They emerge from there. And in turn they run parallel. Right? They run parallel to their respective. Means x is 0. X is 1. And if you see, this is, let us say 0 0.1, 0 0.2, 0 0.3, 0 0.6, 0 0.7, 0 0.8, 0 0.9, just an example. So they will run like this. So these are constant dryness fraction lines, or these green lines are constant dryness fraction lines. What are all these green lines? They are nothing but constant dryness fraction lines. Okay? They are nothing but constant dryness fraction lines. Is it clear? Is it clear? These are nothing but constant dryness fraction lines. Alrighty, that's great. Okay, simple. Understood, everybody? Properties, let me give you properties at the critical point of water. So you need to remember these properties. So what are the properties at critical point of water? So when you are saying at critical point of water, see, your pressure is 220.64 bar or 22.064 megapascal, and then temperature is 373.15 degrees Celsius. Specific 3 it is, not 2, it is 3. Specific volume is 0.00317 meter cube per kg. Okay, understood? So these are the properties. This you need to remember. Okay, this you need to remember. Logic is clear? Yeah, it is 3. Just that it's not looking like one. Now it will. Yeah, 373. Got it, everybody? Shall we? Okay, where do you have here? What do we have here? Done this properties, this and that, blah and blah. Okay. Also, let's put a note point over here. Here, logarithmic, straight line, again logarithmic, right? So what is it? Sensible heat. Please tell me, what is it? Sensible heat. What is it? Latent heat. Isn't it? And what is it? Superheat, or again sensible heat. For boilers, this is done in an economizer. The part of boiler in which we do the sensible heating in order to bring it to this point is known as economizer. This part is given in boiling drum or boiler drum, and this is done in superheater. There are three types of superheaters: convective, radiative, and pendant. So yeah, these all are there. Okay, everybody, say yes or no. These are simply for the boilers. Sometimes it may ask you, and please do this. Take a screenshot. Please take a screenshot, then we'll move forward. Please take a screenshot and then we'll move forward. Is it clear, everyone? Is it clear, everyone? Okay. Okay. Now we are going to start property calculations pretty soon. Okay, great. But before that, let me finish something. Note point once again. Note point once again. What is it? Please pay attention. Please pay attention. What are the note points? हाँ, देखो. This is how heating is done at constant pressure. Now let me mark this as a point A, that as a point B. No. Let me follow the same trend I'm going to follow afterwards. B, this some point C in between. It can be anywhere depending on the dryness fraction value. D, and there is E. Okay, so, and this temperature is saturation temperature. Since B, C and D are all collinear, they are collinear points. It means that at same temperature, they have same temperature, and वैसे भी phase change occurs at constant temperature. Therefore, TB, TC, TD, and TB, TC, TD, they are all equal, which is equal to saturation temperature. Yes or no? Yes or no? Great. Also, this is liquid. Everywhere we have liquid, liquid plus vapor, and then we have vapor. You can see TB is greater than TA, or TA is less than T saturation, because TB is T saturation, means A lies in the subcooled region. Where will A lie? Subcooled region or undercooled region. So how do we define undercooled region? If the temperature of any point is lower than this, it will be known as subcooled region. So up till here we have subcooled region, and this is your wet region. Now here we define degree of subcooling. DO sub. We calculate degree of subcooling, that will be temperature difference. Simply saturation temperature minus TA, that will be degree of subcooling. Next point. If you pay attention, TE is greater than TD, which means that TE is in turn greater than saturation temperature. If that is the case, then E lies in the superheated region. What is the meaning of superheated? It is beyond saturation. The temperature is increased beyond saturation temperature. So E lies in the where? Superheated region. E lies in the superheated region. Okay? About D, in the superheated region. Is it clear? Okay? I have written wrong, kya? T saturation minus TA, degree of subcooling. Degree of subcooling, saturation minus A. Now it will be E minus saturation. Okay? So we have superheated region. Now I am going to define degree of superheat. What is it? DO sup, and that should be T minus T saturation. Simple. Understood everybody? T minus T saturation. That is how we are going to define it. Logic is clear? Is the logic clear, everybody? Say yes or no. Say yes or no. Now we can move on to further properties calculation. We will do properties calculations over here. In the next 20 to 25 minutes, we'll do that. And around 4:30, we'll take a break. Okay? After 20-25 minutes, we'll take a break because this chapter will be over. Okay? Shall we move forward? Properties calculations. Now, which all properties are we going to see? Number one, enthalpy. That too specific enthalpy. Number two, entropy, and that too specific entropy. Number three, internal energy, that too specific internal energy. And number four, volume, that too bacha specific volume. Okay, we'll do that. We'll do that without any shadow of doubt. Please, I request you guys that you please take the screenshot. Please take the screenshot. Yeah. Okay, done. Shall we? That's great. Now let's move forward. Let's move forward. Let's deal with a few things over here. Let's now deal with a few things over here. In this, what are we going to talk about? What are we going to say? And what all are we going to start? So now, in this, if we see degree of subcooling superheating is done. Now let me draw, and please pay attention. This is ultra important, my dear students. TS diagram. Same. A, B, C, D, E. Alright, A, B, C, D, E. Now you have A, B, C, D, E. Now what will happen if you have A, B, C, D, E? Something which is very like unusual. And what that specific thing is? That, my dear students, subcooled, wet region, vapor dome and superheated. Now in this case, in this scenario, let's first go for enthalpy calculations. Okay. All right. Now see, common knowledge. Common knowledge means which will be applicable everywhere. Okay. Now at constant pressure, del Q equals dH equals Cp dt for unit mass. Yes or no? In case of unit mass, it is equal to Cp dt. Please tell me yes or no. Cp dt. dH equals to what? Cp dt. Right? Constant pressure del Q dH which is equal to Cp dt. Unit mass के लिए. अब मेरी बात ध्यान से सुनना. Just please pay attention to me. Now. Okay. You remember, no? Means delta H can be written as Cp delta T. That's all. That's all what we require. That's all. That's all you need to understand. Simple, no? Simple? Simple? No problem? Okay. Let's see. HB. Number one, HB. HB will be HF or enthalpy of saturated liquid. Why? Because this B point lies on saturated liquid diagram. So it will be HF equals to enthalpy of saturated liquid. HB, HF will be the enthalpy of saturated liquid. Say yes or no. Enthalpy of saturated liquid. It is as simple as that. And it will always be given in the problem. It will always be given in the problem, or from the stream table you can find out. Directly it will be given. Don't worry about it. It will be given directly. You don't need to worry. Okay? It will be given directly. You don't need to worry. Number two. HD. Now this is Hg. Simple. Enthalpy of what? Saturated vapor. So either it will be given, or Hg, which is HD, can be written as HF plus latent heat of vaporization. Say yes or no. HF plus latent heat of this latent heat of vaporization, if I add in HF, I'll get HD. Yes or no? I'll get HD. Simple. If latent heat of vaporization and HF are given, don't worry, you can calculate this. If directly it is given, balle balle, no problem. Now number three, HC. Okay, total HC, H of liquid plus H of gas. Now please understand. Please understand. This is total. This is of liquid and this is of gas या vapor. See, at this point C, we have a mixture of liquid and vapor, right? We have a mixture of liquid and vapor. Great. If we have a mixture of liquid and vapor, now then what happens? What happens? The total enthalpy at C point, the total enthalpy at C point will be what? This total enthalpy at C point will be what? It will be due to liquid as well as due to vapor. Yes or no? Now great. Which means that m times of Hc equals mass of liquid times of Hf plus mass of vapor times of Hg. सही बात है? Yes or no? I can divide it ml by m, mg by m, Hg. What can I write? M minus mg. अरे बाबा, this can be written as m minus mg. ml can be written as m minus mg. Hf. mg by m, Hg. 1 minus x Hf. X Hg. This we have studied. mg by m is x. So now we have Hf minus x Hf plus x Hg. So what it will be? Hf plus x Hg minus Hf. Got it? Hc can be written like this. Say yes or no. Hc can also be written like this. So these are the formulations, and these formulations you might have studied many a times, but difficult to recall. Don't worry. Also it can be written as Hc equals to Hf plus x Hfg. Now what is Hfg? What is Hfg? Where Hfg is Hg minus Hf. Hfg is what? Hg minus Hf. Got it everybody? Hfg is Hg minus Hf. Understood? Say yes or no. Understood everyone? What is Hfg? It is nothing but Hg minus Hf. Please take the screenshot. Please take the screenshot everybody, then we'll move forward. And do tell me whenever you have done with it. Do let me know please. Okay. Okay. Great. Now it is done. Number 3. Number 4. Now we are interested in HA. Now we are interested in HA. Yes or no? You tell me. Is A less than B? TB is greater than TA? Yes or no? TB is greater than TA, and at constant pressure A and B lie on constant pressure line. Lie. Constant pressure line. They both lie. Means enthalpy is a function of temperature only at constant pressure for liquids. For liquid. Sir, A वो HF था या HL? HF and HL are same, no? See, what have I told about HF? Enthalpy of saturated liquid. HL HF is same. HL HF is same. Okay? Whether you write for liquid, because I'm not writing L because you will get confused. Earlier I have used F. So some people might ask, sir, whether it is what? Please tell us. Understood now? Now it is a function of temperature only. Is it? Yes, at constant pressure. Means HA, HB will be greater than HA, which means HB will be, if I want to equate, see, if I want to equate to HA, I need to subtract something, HB minus delta H. And already we have calculated delta H, Cp delta T. Already we have calculated delta H, Cp delta T. Done. HA equals to, never been so easy, always been so easy. It's just that you have not seen it like that. CPL. Why am I writing CPL? And that will be degree of subcooling. T saturation minus TA. Why am I writing CPL? Because CPL stands for what? Chennai Premier League? No. CPL stands for what? It stands for specific heat at constant pressure for liquids. Understood, yaar? Understood, yaar? Yes or no? Great. Let's move forward. Number fifth. Okay. Number fifth. What about number fifth? H D E E. It's simple, Baba. T is greater than TD. Oh, they are at constant pressure. Enthalpy is a function of temperature only, because it goes in gas, ideal gas, blah blah blah, which means that HE is greater than HD. If I need to make it equal, I need to add something, delta H, or HG plus delta H means HG plus CPG, degree of superheating. How much is that? T minus T saturation. Logic clear? HE. Understood? Understood, everyone? Say yes or no. HE equals to HG plus CPG TE minus T saturation. Is it clear, everybody? You make easy. Thank you. I have made it easy. I put it in between. Okay. Understood, everyone? Easy peasy, lemon squeezy. Now you will go for number 2. Now it will be very easy. Entropy calculations. Okay, dokie, aloo loki. Entropy calculations. Okay. What do we have here? TDS equals DH minus VDP. Ayyo, constant pressure. TDS is a Cp dt by T. And what I guess delta S, Cp ln T final by T initial. Over here, what am I going to get? I'm going to get logarithmic variation. Yes or no? I am going to get what? Logarithmic variation. If I am going to get logarithmic variation, now I will solve very easily. Number A. What about number A? Number A is HB. Ayyo, not HB. I need SB. SB equals to SH. SF hoga? It will be SF. Why? It is saturated liquid entropy. And it is always given. It is always given. From the stream table you can find. So it is always given. You don't need to calculate it from somewhere. Number B, SD. It is SG. Entropy, specific entropy of saturated vapor. This is either given or, and based on this, there is a question which we have left in your previous year book, 4.112, I guess. 4.12 is there. If you check, you will now be able to solve. Means SG equals to SF plus delta S. See, SF plus delta S, if I add, how much is this delta S? It is happening at constant temperature. Latent heat of vaporization upon saturation temperature. Finish. LHV by T set. Understood, everyone? Yes or no? Latent heat of vaporization. नहीं 10 kg ऐसा कुछ है, देखना उसे. 4.12. That is the first one which you are saying. Please take a screenshot, my dear students. Take a screenshot, everybody. Please take a screenshot. Okay? Great. Great. अमोनिया वाला है, छागे गुरु. Now HG, sorry, SG, SF, Hg minus HF upon T saturation. You can write it down in this way as well. Why? Because what is latent heat of vaporization? If you see, what in reality is latent heat of vaporization? Hg minus HF. Yes or no? Simple. Number 3. Should I simply write SC as SF x Sg minus SF? Can I write it down in this way? Or I can also write SC barabar SF plus x times Hg minus HF upon T saturation. Array, say yes or no? Yes or no? There is no need of deriving again and again. You'll derive it by same methodology. There is no need to derive the same sequence over and over again. It doesn't make sense, does it? No, not at all. I mean, not to me, obviously. Okay, then sorry, that must have been C. Okay, now let's talk about D. What about SA? We can visually see actually SA is less than SB or SA is less than SF. You can visually see this. You can visually see this less than SB, SXX. Yes or no? Is it clear? You can visually see that. Now, see, if you want to make it equal, then definitely something must be subtracted from the larger value. What it will be? Delta S. And delta S we have already calculated. Delta S, we are very chalak. SA equals SF minus CP liquid ln. Arey baba, it is already done. T saturation by TA. Say yes or no. Is it clear? Ding dong ding, ding dong, ding dong, ding dong. Got it? Number E. Number E. So what is SC? Okay, we can visually see that SC is greater than SG. See na baba. SC is greater than SG. Okay. So now what can I do? SE equals SG plus delta S. Oh my dog. Now why am I writing delta S again and again as this format? Because this is at constant pressure. SE equals to SG. Simple baba, CPG. It's not that I'm saying it out of respect. CPG. No. It's just that it is CP gaseous, CPG. Not out of respect. ln T by T saturation. Finish. Yes or no? Yes or no? Finish. I mean, very easy, isn't it? Let's move on. Number 3. Specific internal energy. U. small u. Okay. Now see, for liquids, don't you see that Cp and Cv are equal? Huh? And for superheated region, ideal gas law is valid. In superheated region we can apply ideal gas equation. Okay, I'll tell you on this note. So delta U will be Cv delta T. Delta U will be Cv delta T. Simple. See, what am I saying? Please keep it in mind. Liquid plus vapor. Now see, PV equals to PV is not equal to MRT. PV is not equal to MRT means ideal gas law cannot be applied. PV equals to MRT can be applied, right? Means ideal gas law, IG law, Indira Gandhi nahi, ideal gas law is applicable only in the vapor region or superheated region. Got it? That's why not. Is it clear? So I can apply it there. Now I'll say number A. SB was there, no? SB. Sorry, UB. That will be UF and that will be given. Simple. B point. UD. That will be UG. That will be given. C. UC. That will be calculated and that can be derived. Yes or no? We have already derived. What about U? What is there? UA. So don't you think whether it is liquid or solid, liquid, Cp or Cv, we don't consider it. So UA will be what? UF minus delta U. And how much is delta U? Cv or Cp liquid or whatever. Cp Cv is same. Cv liquid T saturation minus TA. Yes or no? E. UE equals to UG plus, it will be added, Cv gaseous T E minus T saturated. Because for an ideal gas, U is a function of, I have explained it to you that U is only a function of temperature. Yes, exactly Kadri, exactly. क्या बताया था मैंने? बॉइलिंग पॉइंट से कंपेयर करोगे, सो यहां से शुरू करोगे तो इधर हाई टेम्परेचर आ गया, एंड क्रिटिकल प्रेशर से कंपेयर करो, लो प्रेशर, हाई टेम्परेचर, आइडियल गैस लॉ कैन बी वैलिड. Got it? Understood now? So these are the formulations for U, specific internal energy. Got it, everyone? You just have to keep in mind that for liquid and vapor you need to separate. Okay? Is it clear? Everyone? Everyone? So let's do one thing. I know you don't have this much habit of long classes, right? Almost all the properties are done. Let's take a break. Let's take a break of 20-25 minutes. Okay, 25 minutes is good. Or let's say we are taking it off 28 minutes. So we'll meet at 5. Will that be fine? We'll meet at 5. And please do come, everyone. I expect everybody to rejoin. Okay, I'm giving a break. Also, I'll take the medicine and have all. So I'll giving the break. Will that be fine? Will that be okay with you guys? Perfect. Fine. So we'll meet at 5 sharp. Please be here only. Thank you. Let's meet at 5. Today we'll complete it. Thank you. Hello everyone. It's good to be back. Okay. So we have come on our stipulated time only. So please share it everywhere. Please share it that the session has finally started. Please tell it to everyone. I'm requesting you. Please do tell it to everybody. And then we'll move forward. Please share it everywhere so that we are going to start it. Okay? That the class has been resumed. Please join. Simply write it. Wherever you have your groups and all, simply write that the class has been resumed or the marathon has been resumed. Please join everyone. Okay? Now, so there was fourth property remaining, and that was volume. To be very exact, specific volume. We are more concerned about this. Yeah, we are in end game now. That was infinity war. We are in end game now. Let's see. In this, have a look. For liquids, don't you know that for liquids, volume is constant, means VA, VB, VF. We can say that? Yes or no? Because why? The liquids are highly incompressible. Say yes or no? The liquids are what? Highly incompressible. That is why. Since the liquids are incompressible, that is why we are doing this. Is it clear? You are so punctual. Yeah, I mean punctual with the timing. I have to be. Otherwise, students will not respect me. A man is always respected by his virtues. Anyways, so whatever I am demanding from you, I must also follow the same in my life. That's what I believe. Okay, so VA equals VB equals VF, right? This is A. Let's B. VF plus X. This you know already. There is no need of proving it. VG minus VF. Yes or no? We can do this. Tell me. And 1, 2, 3. One more is remaining, I guess. VC. VD. Option C. VD. What is VD? It is VG actually. And it is always given. This one is also given. Great. Now, let's talk about VE. See, since E lies where? In the vapor region, or I should rather say super heated region. This lies in the basically superheated region. Yes or no? Is this a specific volume? Yes, it is a specific volume. Up till now we have all considered specific terms. Sumit, are you okay now? I can understand your dilemma. I am also having a fever. Not 101, but it is around 99.5 something. It is between 99 and 100. Anyways, this is heated region. Okay, superheated region. Over here is ideal gas law valid? So is the ideal gas law valid? Yes, the ideal gas law is valid. What is the ideal gas law? PV equals to RT. At constant pressure, volume is proportional to T. Means VE by VG will be TE by T saturation. Say yes or no? Yes, this we can say. This we can say. Is it clear? Simple. So these are all the properties which are to be calculated. These are all of those properties which we were talking about, and these are all of those properties which we are concerned about Okay, understood? That's great. I'm glad to hear that. Anyways, so property calculations, these were the formulae, and I hope that you guys must be familiar with all of these formulae and you will be comfortably remembering them. Over the period of time when you are going to do certain questions, when you are going to do revisions and everything, you are going to definitely remember all of them. Understood? Let's come here. Let's revert back. So my dear students, that is fourth volume. Let's now move on to the next part. Let's now move on to the next part and see a few things here and there. Certain points. Number one, triple point on a PT diagram only is a point. Yes or no? We remember this? Triple point on a PT diagram is point. Number two, triple point on PV and TS diagrams is a line. What is it? It's simply a line. It simply follows a line. That's all. And triple point, this is also important, on UV diagram. What is UV diagram? Internal energy specific volume. UV diagram is a triangle. Yes, it is represented by a triangle. Although this is not in your course, but you should know this fact. Anyways, number 4. At triple point of water. And this triple point of water is actually the reference for steam tables. SF is taken as 0 and UF is taken as 0. See, let me tell you. The fact is that these are properties, right? So calculating the exact values of these properties is very difficult. It is very difficult to calculate these exact values of the properties. So what can you do? You can only calculate the changes. Only you will be able to calculate the changes. So the changes, for those changes I need to assume somewhere, at least somewhere, the value of that property is 0. So hence I have taken SF as 0 and UF as 0. Means I have taken triple point of water as reference, right? So whenever you go and purchase steam table, whenever you want to go and purchase that steam table booklet, just simply do one test. What's that? Look for the temperature column. In that temperature column, the very first must be 0.01 degrees Celsius. Now, if at 0.01 degrees Celsius, the values of UF and SF are 0, then that steam table is correct, purchase it. If it is not, then don't buy it. Okay? Is it clear? So, UF and SF are taken as 0 at the triple point of water. Logic is clear, everybody? Is the logic clear, everybody? Please tell me. Take the screenshot. Would you like to do a few questions? Would you like to do some questions? Okay? Great. Great. Let me take that booklet, and I think you might have taken the screenshot. Okay. So now let us deal with the question which we left in the name of this chapter. And that question is 4.12, that ammonia problem. You remember that ammonia problem? 4.12. That is IIT Kharagpur 2014. A closed system contains 10 kg of saturated liquid ammonia. M equals to 10 kg. saturated liquid ammonia. Okay, at 10 degrees Celsius or 283 Kelvin, right? Convert the entire liquid into saturated vapor at constant See, you have been given with latent heat of vaporization, net, total, means not per kg, in megajoules. Megajoule, 16.2 megajoule, right? And entropy of saturated liquid, SF, 0.88 kilojoule per kg Kelvin. Now what has been asked? VSG will be what? So in these kind of problems, I have already told you SG is equal to SF. We have established this. Yes or no? Hg minus Hf, or latent heat of vaporization I should say, upon saturation temperature. So what is latent heat of vaporization? That is latent heat of vaporization total terms wala, net over mass of the system. Is it clear? Over mass of the system. It will be in kilojoule per kg because this is in K. Understood? So now SG equals SF 0.88 plus 16.2 mega means 16.2 10 to the power 3 over, that is megajoule, upon mass 10 into temperature 283. Now you do it, you will get SG. Whatever be the value, you will get it. Understood? Understood? And this we have studied just now. Haven't we? This we have studied just now. Please tell me. Is it clear, my dear? Is it clear, yes or no? Is it clear? Let's move on to with the next question, which is properties of pure substances. Great. And let me give you one question which is very beautiful in my eyes. See, where is it? Yes, 6.8. It's a very beautiful question. 6.8. Let's deal with this problem. 6.6043. Good. That is kilojoule per kilogram Kelvin. All right. This is what you have. Now, can you guys read this question out? Please try and understand this question. 6.8. And after this, we'll take one more question and then we'll move forward. Okay. Rest I'll give you as homework and then I'll discuss it as well. Don't worry. I'll discuss that question as well. Those questions, means previous year questions of GATE. Okay. So please tell me, how about it? How about it? 6.8. Let me do it. See, something is given. Mass is given, 10 kg once again, and the volume is 0.25 meter cube, isn't it? 0.025, I guess. Yeah? Meter cube. And specific volume is given as critical specific volume 0.00317 meter cube per kg, isn't it? Now what about specific volume? That will be total volume by mass. That means 0.025 over 10, which is equal to 0.0025, and it is meter cube per kg. That is your specific volume. Is it clear? You tell me. Isn't the specific volume less than critical specific volume? Is it less than that? Therefore, let's draw a PV diagram. Okay, let's draw a PV diagram. and I believe that PV diagram looks like this. Huh? Okay. Since the cylinder is rigid or the chamber is rigid, rigid chamber means what? No change in volume. Okay, means volume is constant. Volume is constant. Heating occurs. If heating occurs, then volume proportional pressure proportional temperature, means as temperature increases, pressure increases, means it will go like this. And it is, see, you will understand immediately. That is 0.00317 meter cube per kg. Alright, and that, my dear students, is 0.0025 meter cube per kg. Okay, simple. This is 1 to 2, is it not? This is 1 to 2. Now let me give you a context. If you see, there is a constant dryness friction line. If you see, that is another constant dryness friction line. Yes or no? All right. X2, X1. So X2 is less than X1. Means dryness fraction decreases. Mass of liquid decreases. Mass of liquid nahi. Mass of gas decreases. Mass of liquid increases. Understood now? Is it understandable? This is very important question. Why? Because it takes use of your brain. See, it is given that the chamber is rigid and heating is done. Means rigid chamber means no change in volume. No change in volume means constant volume. If there is a constant volume, means pressure is pressure is proportional to temperature. As temperature increases, pressure increases. Yes or no? Temperature increases, pressure increases. That is the case. All right. This increases. Finish. 1 to 2. That's it. Okay. Dryness fraction. See, it is 0. Dryness fraction of this part is 0. And if I am talking about X2, it is near to 0, means X2 is less than X1. X decreases means mass of gas decreases, means mass of liquid. So the liquid level will rise. Understood? In this case, liquid level will rise upon heating such a system. Okay. Say yes or no. Say yes or no, everyone. Please tell me. Please tell me and take the screenshot. Please tell me and take the screenshot. Is it understood? अरे बोलो यार. Is it understood? Yes. Great. बहुत बढ़िया. Shall we move forward? Okay. Now, I am giving you this as homework. Okay. And also, see, tomorrow there will be a holiday. Day after tomorrow it will be a test. Menti. Tomorrow there is a holiday. Day after tomorrow, because subject is finished, you take time to do the questions. Okay. And on Tuesday you have a Menti. And from Wednesday, which subject should I start? Should I start heat transfer? Tell me. Should I start heat transfer? You guys will have fun. Let me start heat transfer from Wednesday. Okay. Let me start heat transfer from Wednesday. Will that be fine? Will that be fine? Heat transfer, no? You guys will enjoy it like anything. Sir, if pressure directly proportional to temperature, then how LPG gas is compressed, it became Milan. That is when volume is constant. But in gases, is the volume constant? Is the volume constant in gases? After applications will do, after heat transfer will do applications. Okay, after heat transfer will do applications. Thank you, Mank. Thank you. So what am I saying? Understood? Understood? Milan. Simple. Over there, pressure, volume was constant. But in gases, what do? We decrease the volume. We are changing the volume. Simple. Shall we move forward? Shall we move forward? Say yes or no. No, I am starting with heat transfer. Okay. Next is, कौन सा यार? Thermodynamic relations. Thermodynamic relations. Okay. Thermodynamic relations. Now, we'll do these thermodynamic relations. Okay. This is a very important chapter. And after this chapter, it'll be over. It is something around of, I guess, 1.5 hours or 2 hours it will take maximum. Okay. So please bear with me for another 2 hours or 1.5 hours so that today's end game will be over. Okay. So let's talk about thermodynamic relations. So what all are thermodynamic relations? How do we understand thermodynamic relations? And there were some topics here and there which I told you, right? For example, I'll prove this after we study thermodynamic relations. I'll prove that after we study thermodynamic relations. So these were the few things here and there which you need to study, right? So thermodynamic relations, number one, some mathematical tools. Let's use some mathematical tools. Let's check out some mathematical tools. Number one, theorem number one. Let's say theorem number one. So what does theorem number one say? Mathematical tool number one, theorem number one, what does it tell you? Conserve volume constant and pressure increase, temperature increase. One example of this, please. This was the example, yaar. Have you not read this question? This was the example. For example, a pressure cooker. A pressure cooker. What happens in a pressure cooker? What happens in a pressure cooker? Is the volume constant? Yes. Is the volume constant? Yes. Do you do the heating? Yes. Does the temperature increase? Yes. Does the pressure increase? Yes. Then only to release the pressure, that valve is given or that vessel is given. Simple. When the pressure reaches to an optimum or operation extent, that steam goes out. Simple. Kettle in which tea is prepared, boiler, there are many examples. Okay. Many examples are there. Anyways, theorem number one. See, if we have dz as mdx plus ndy, right? I am saying that I can write dz as mdx and ndy. Now tell me, have you understood? Milan, example पूछा, बताओ ना, समझ में आया या नहीं? dz, this z is what? Exact differential. Exact differential. Okay. What is it? This z or z? That is an exact differential. Mass of gas increase in case. दिमाग खराब है क्या? हैं? दिमाग खराब है? यहाँ पे क्या हो रहा है? ये समझ में नहीं आ रहा आपको? We are talking about total mass. नहीं समझ में आ रही है? We are talking about total mass. Please understand this. We are talking about total mass. if the total mass of the mixture is taken, that mass of the mixture is constant. Is it not? That mass of the mixture is constant. How is the mass changing? How is the mass changing? If you take total mass, mass of the mixture is constant, na? Is it or is it not? So this is an exact differential. So if this is an exact differential, we can say del m. This you must have studied in your partial differentials, yes or no? Del m by del y at constant x, del n by del x at constant y. Let's not write it as equation 1. You will get confused. Let's not write it as equation number 1. So you understand what I am saying? Theorem number 1, what does it tell you? Del m by del y at constant x, del n by del x at constant y, they both must be equal. That both must be equal. Yes or no? Yes or no? Got it? अच्छा, चल शेयर करो यार, शेयर करते रहो तुम लोग. You guys keep on sharing. I don't know what is wrong. Next. Theorem number 2. Let's say z is a function of x and y. Simple mathematics tells you dz can be written as total differential, can be written in the terms of del z over del x, y constant dx, del z over del y, x constant dy. Total change is the sum of partial changes, right? Total change is equal to the sum of partial changes. Okay? Sum of the partial changes. Say yes or no. Sum of the partial changes. Is it clear? Total change is equal to the sum of partial changes. Fine. There is also, we know. Now, theorem number 3. Let's say z is a function of x and y. Again, now you can also write del x by del y constant z times del y by del z at constant x times del z by del x at constant y equals minus 1. Equals to what? Minus 1. Negative 1. So this, my dear students, is your third theorem. And that theorem is also used when we study. Is it clear? That theorem is used as well. So there are 3 theorems. Using these 3 mathematical theorems, we are able to solve these kind of thermodynamic relations. So these theorems are the key, and these theorems are very important. Please take the screenshot, then we'll move forward. Please take the screenshot, then we'll move forward. Shall we move forward? No, I am not great, yaar. I am not great or anything. It's a simple thing. You should know this. Anyways, shall we move? Shall we move further? See. Now we are going to deal with Maxwell's equations. Maxwell's equations. See. I'll derive 2. I'll give you other 2 as homework and I'll tell you the trick. Will that be fine? But don't worry, I'll tell you the entire Maxwell equations, all the derivations. In case you forget, you'll always blame me. So let's deal with this one. TdS equals du plus pdv. Alright. Can I write du as TdS minus pdv? Of course. Now from theorem number 1, can you please tell me, is du an exact differential or inexact? It is exact. It is a change in property. So du is an exact differential. Therefore, m dx, m dy means del t over del v at constant x, constant s. See, del minus p. Why minus p? Because the value of n is negative here, over del s with constant v. Means I can say that del t by del v at constant entropy minus del p over del entropy at constant volume. This is first Maxwell's equation. I'll tell you the trick, don't worry. I know you will be afraid of this. You will be nervous by simply looking onto this equation. But let me tell you, after some time it will be a cakewalk for you, right? It will be a walk in the park for you. Next, another TdS equation we have, dH minus VdP. Don't we have this? Yes, we have this. Now what do we do? TdS equals dH minus VdP. Now in case of this, what am I going to do? I am going to simply dH TdS plus VdP. Can I do that? Yes, of course I can. Now again from theorem number 1. So from theorem number 1 I can say that del T over del P at constant entropy equals del V by del S at constant pressure. This is second second Maxwell's equation. Now you must be very afraid by now. Sir, how are we going to remember them? Don't worry, I am here. Let's talk about Gibbs function. You remember Hertz, H minus Ts, right? Let's simply differentiate it. So upon differentiating, what are we going to get? Upon differentiation, we are going to get dg equals dH minus TdS and minus SDT. dH minus TdS. Okay. dH minus TdS is VdP. dH minus TdS is what? VdP. Yes or no? We know this from there. So what are we going to get? dg equals VdP minus SDT. And that, my dear students, where you can use theorem number 1, again from theorem number 1st, what are you going to get? Del V over del T minus ka, I am simply using this, okay? Del S over minus sign I am using, del P at constant T, equation number 3. Got it? I told you this Gibbs function will be used to derive Maxwell's equation as well. Am I clear? People are thinking that, sir, it is not mentioned in our syllabus of GATE examination. But let me tell you one thing, my dear students. This was asked both in XC as well as mechanical paper of last year. So this is a very important topic which you should not forget, I believe. Anyways, next up you have Gibbs Helmholtz function. We denote it with F foots U minus Ts. Now please differentiate it. So upon differentiating, what are you going to get? Please see. Upon differentiating, you are going to get df du minus tds minus sdt. And by the way, du minus tds will be, because tds is equal to du plus pdv, so it will be minus pdv. So df becomes what? Minus pdv, negative pdv, negative sdt. Say yes or no. It will be all negative. Is the concept clear? Is the concept clear? Therefore, from theorem number 1, you can use theorem number 1. So using theorem number 1, you get minus del P over del T at constant volume equals negative del S over del V at constant temperature, which I can say negative can be cancelled out on both sides. Del P over del T, constant V, del S over del V at constant T. Say yes or no. This is equation number 4. Is it clear? Is it clear, everybody? So you have 4 Maxwell equations. 1, 2, 3 and 4. You have 4 Maxwell equations now with you. Don't you have? Please tell me. Now you have 4 Maxwell equations. Is it clear, everyone? Is it clear, everyone? Now please take a screenshot. Please take a screenshot. Please take a screenshot. I think you might have. Okay. Now you must be very confused. Sir, how to remember these bhokal things? Okay. Don't worry. I'm here. I'll teach you. You just need to remember today's Teachers Day, and you need to remember tumhare means yours, pyare, loving, Varun means me, sing or sir. So tumhare pyare Varun sir. You guys love me, right? Don't you? You should. Tumhare pyare Sir Varun. Let me give myself some more importance. Sir Varun. तुम्हारे प्यारे सर वरुण. नहीं? You guys love me, right? Yeah. So now, suppose you guys got successful, and I'm very happy. I came to visit your home. I came to visit your home. Is there any? I came to visit your home. Fine. So you told me to, sir, please sit, sir. I sat. तुम्हारे प्यारे सर वरुण sat like this. तुम्हारे प्यारे सर वरुण sat like this. तुम्हारे प्यारे सर वरुण. Okay, I told you, I asked you that, okay beta, show me your home. It's a very magnificent one. I love it. I want to see it. Then you took me, sir, please, it will be my pleasure. Come with me. I came with you. I went with you. So that means del T over del P, del V over del S. Okay. So whatever is not there in the denominator means whatever is there in the other denominator will be as constant. Will be as constant. Okay. Simple. Okay, we went there. We went across your house. Let's come back. So when we'll come back, it'll be del P over del T. Isn't it very simple? Equals del S over del V. What is in front of this? T. V. Simple, Baba. Simple, Baba. Now, definitely, we have moved across your home. Now, We need to go up as well. You want me to see your terrace as well, because you have some roof garden, you have a jacuzzi at your home on the roof, you have amazing roof, right? So you took me there onto the roof, not to push me, but you took me there. Anyways, del V by del T equals del S by del P. Pressure, temperature, yes or no? And will come down as well, will come down as well. It will be del T by del V, del P by del S. So in front it is S, in front it is V. Isn't it amazing? Yes or no? Okay. But now you will say, sir, there were two negative terms as well. Let me tell you the story for that. When I visited your home, obviously I'm old. Let's say I'm 40-45 years old. Then I have arthritis. Then definitely walking over stairs is difficult for me. And walking over stairs is very difficult for me. So going up and down is difficult, is not good enough for me. That means it is negative for me. It is negative for me. Walking up and down is negative for me. Simple. Take the screenshot. Is the story fed in your mind now? Is the story fed in your mind now? Now can you remember? There is a best trick in which you can do. Aag laga di aag. Understood everybody? Understood everybody? Yes? Let me remind you, you have become successful. I went to your home. Who went to your home? Tumhare pyare Sir Varun. Your loving Sir Varun. It's me. And you make me sit in your home. Tumhare pyare Sir Varun. Tumhare pyare Sir Varun. Okay. Now there is no need to cross clockwise, anti-clockwise, this, that, falana, dimkana. But never. No need. This, that, blah, blah. No. Tapasvi. What is tapasvi? No. No tapasvi. Tumhare pyare Sir Varun. Now see. Del T over del P, del V by del S. We went to see your home across. Then we came back. Simple. Moving horizontally is not difficult for me. Why? Because I'm old age now. When I visited your home. Not now. When I visited your home. Similarly, we went up to see your roof. We went up to see your roof. It was very lavish. We went there and then we came down. Moving up and down is difficult for me because I have arthritis or some orthopedic problem. It hurts my knees. Okay. Negative sign will be there. You please match them. Please match them. For example, if in the problem it asks you that, beta, tell us del P by del S. Del P by del S at constant volume will be equal to what? Del P by del S at constant volume will be equal to what? What? How would you do this? You will definitely be confused in exam. Then you will bring me. You will imagine me. Automatically you are seeing this is S by P, P by S. Okay, fantastic. First of all, it is equal to T by V at constant S, by the way. And also it is negative. Why? Because we are moving up and down. Simple. In a fraction of second you can remember. Yes or no? So, tumhare pyare Sir Varun. Finish. Can you remember it? Can you remember it? Of course you can. Of course you can. I know that. Okay, everybody? Please take the screenshot now. Now take the screenshot. Now take the screenshot, please. Now take the screenshot. I hope that you never forget. I hope that you never forget, especially in your exam. Especially in your exam. Okay. Now we will deal with TDS equations. TDS equations. Let me start TDS equations. Let us start with घर बुला लोगे चलो बढ़िया. Let us start with TDS equations, right? So what are TDS equations? How we are going to deal with TDS equations? How we are going to see them? See. You will say that, sir, we already know this. du plus p dv. Yes or no? Then ds can be written as du by t, sir, p by t dv. But I know already. This you will convert with pv is equal to mrt. No, we don't. Now we won't. Because now we are going to calculate it for real gases. Okay. Now we are going to calculate it for real gases, not ideal gases. Ideal gases we know how to deal with, right? But now we are concerned about real gases. Okay. Please tell me. Now we are concerned about real gases. Let's move forward. ds is this. Now if we have this as ds, then entropy can be written as a function of temperature and volume. Because du is a function of temperature, dv stands for change in volume. So means total entropy change will be a function of changes in temperature and volume, or I can simply say that entropy is a function of temperature and volume. Now use theorem number 2. Theorem number 2. What does it say? ds z function of xy, ds del s by del t at constant v dt plus del s by del v at constant t dv. Yes or no? Multiply whole of the equation by temperature T. Okay, let us multiply the temperature by whole of the equation by temperature T. If we are doing that, we are getting TDS equals T times del S by del T constant V dt plus T times del S by del V at constant T dV. Yes or no? Yes or no? यही आ रहा है? This is what we are getting. This, let us say, equation number A. See, these A, B, C, D, these kind of equations you don't need to remember. You don't need to remember. You need to remember only equation 1, 2, 3, 4, 5, 6, so on. Okay. Now, we know this TDS equals to du plus PdV. Great. This is 0 for constant volume. If the volume is constant, means TDS equals to what? Du. Means ds equals to what? Cv dt by t. Why? Or I should say that TDS equals to what? Cv dt. Why? Because at constant volume du equals Cv dt for any gas. Yes or no? Be it real or ideal, it doesn't matter. We can always write it. Understood? Now T times ds by dt is Cv. Can I write it in this way, that T times del S by del T at constant volume? This is the same. For constant volume only we have calculated. This becomes Cv. So I believe this equation number B gives you this. Okay? Also, from Maxwell's equation, from Maxwell's equations, if we see from the Maxwell's equation, what are we going to get? From Maxwell's equations, remember, please remember, this you need to replace. So तुम्हारे प्यारे सर वरुण, this is S by V. S by V means del S by del V equals to del P by del T. अरे बाबा, del S by del V, del P by del T, simple. Got it? This is at constant T, this is at constant V. Equation number C. Substituting from B and C in A. When you do so, you have this TDS equation as CV dt plus T times, in place of this I am writing this, del P over del T at constant V dV. This is equation number 50. You need to remember this. Equation number 50. You need to remember this equation. Understood? Understood? This is equation number 5th. This one is equation number 5th. Now please take the screenshot. Please take the screenshot. This is equation number 5th. Acha, don't take the screenshot. Wait. Let me give you the trick. See, what do you have? TDS is du plus pdv. That's what you write. In short, just to remember, you can write it like this as well. Right? So the old TDS equation, the new TDS equation is just like old TDS equation. It only varies slightly. How? See, TDS, this part is same, plus P dV, this part is same. Okay, let us multiply with del, divide by del. Just to remember, right? Multiplying and dividing by del means no sense. Multiplied with T, multiply with T, divide by T. Whatever is here, we'll put there. You are getting it. Okay, so only these blue terms have been changed with the old one. How? Del TT VV. Simple. Okay, that's how you can easily remember. Short trick to solve these. Understood, everybody? Please take the screenshot. Now take the screenshot, please. I request you guys to take the screenshot, please. Must plan hai? Good. Great. Now we'll see the other TDS equation here as well. Now, what do you have here? TDS equals dH minus VdP. You know this. ds will be dH by T minus V by T dP. Now from here you can get to the conclusion that this is a function of temperature and pressure this time. Now use theorem number 2. Using theorem number 2, what can you get? ds, total change in entropy, equals to del S by del T at constant P dt plus del S by del P at constant T dP. This is it. Multiplied with T, multiplying by T. If you multiply the equation by T, what are you going to get? You are going to get T ds equals, what is it? T times del S by del T at constant P dt plus T times del S by del P at constant T dP. Is it clear? Equation number D. Remember A, B, C, D. Got it? Shall we move forward? Same thing we'll do. Same thing. See, TDS dH minus VdP. This is 0 for constant pressure. TDS can be written as Cp dt, because for constant pressure any gas we can write dH equals to Cp dt. Now in this case, T times ds by dt can be written as Cp. or in short I can write T times del S by del T at constant pressure is Cp. Equation number E. Again from Maxwell's equation. Now from Maxwell's equation you have, see, what do you want to replace? This one. So तुरंत तुम्हारे प्यारे सर वरुण, S by P, this time it is S by P, right? It will be V by T. Khatam. Del S by del P at constant whatever minus del V by del T. Simple. Now it is T, now it is P. Okay? Simple enough, Baba. Equation number F. Now substituting from equations E and F in equation D. When you do such, what are you getting? You are going to get TDS equals to T times no. It will be Cp dt minus T times, because it has plus but it comes with minus. Minus and plus will become minus only. Del V over del T at constant P dP. Please pay attention. Please pay attention. This is your equation number 6 now. Now the trick is same as it was for equation number 5. The trick is same. How? Let me tell you. Let me teach you this trick. Once again. You know this, right? dH minus VdP. It can be written like this. And just for the sake of making it easy, it can be written as Cp dt minus VdP. Now I am just simply writing TDS, what I know, Cp dt minus VdP. Okay, great. Now what am I going to do? Del se multiply, del se divide, T se multiply, T se divide, P. Finish. Simple, right? Very simple. So these are your 6 different equations, and actually these equations are going to be very useful. Okay, so you can do them like this. Say yes or no. Is it clear, everybody? Please take the screenshot. Please take the screenshot, then we'll move forward. Please take the screenshot, then we'll move forward. Everybody, please do it. Please do it. Then we'll move forward. Okay. Done, everyone? Done, everybody? Done, everybody? Shall we? Shall we move forward? Great. Great. Now, you tell me LHS of equation 5 equals LHS of equation 6. Why? Because TDS lies on both sides. दोनों तरफ we have TDS, on both the sides we have T in both equations, not on both sides. It makes no sense. In both equations. Equations LHS. Am I right? So that, my dear students, is there. Now what will happen? Now what will happen? Please see. Now what will happen? Please see. Oh God. Now see. Which means RHS of equation number 5 equals RHS of equation number 6 as well. Both are equal. Now what will happen? Cp dt, let's write Cv dt first, because I'm writing 5 here, plus, you remember Cv dt plus pdv means T was there, T, del, pdv, P, right, T, and vdv, Remember, equals. It will be equal to Cp dt minus T del V by del T at P dP. Alright. Now I am just doing Cp minus Cv. This will come that side. Means Cp minus Cv times dt equals. This goes there. That comes here. T common. Del P by del T constant volume dV plus del V by del T at constant pressure dP. Simple mathematics I am doing. Is there any doubt? It's simple mathematics I am doing. Is there any doubt? There shouldn't be. Now can I say this Cp minus C will go there. dt equals T over Cp minus Cv. Alright? Times del P over del T. This will remain same. V dV del V over del T P dP. Alright? Equation number B, C, D, E, F, G. Equation number G. Now, if you see, temperature from here is a function of volume and pressure. Temperature is a function of pressure and volume. Can you see? Of course you can. See, this is simply a coefficient. Coefficient. These are pressure and volume. Understood? 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 See, for this I didn't commit for marathon. Right? I was not there yesterday. I was somewhere else. See, mine also health is not good. So for this, let me tell you, I didn't commit for marathon and completing the syllabus on time. And also I am not committing because of this for the next lecture. I don't want anybody to be leaving now, because that would be super non-beneficial for you only. So please try and understand the gravity of the situation. So temperature is a function of pressure and volume. Is it? Yes or no? Temperature is a function of pressure and volume. If temperature is a function of pressure and volume, then what will happen? If that is the case, see, when I'll do this entirely, I'll give you some homeworks. And those homeworks are very important if you understand this. Now here, I can apply theorem number 2. What does it say? dt is del T over del P constant V dP del T over del V P dV. Equation number GH. Comparing coefficients of dP in equation G and H. Tell me. Please tell me. Please tell me what I am asking you. Understand very, very carefully. Is dt same in both the equations? Yes, LHS is same. And RHS will be same as well? Of course. The coefficient of dP will be equal. Finish. Means del T over del P at constant volume. Del T over del P at constant volume equals to, this is there. See, when you multiply this, then it becomes the whole coefficient. T by Cp minus Cv, and that shall be equal to times del V by del T at constant P. Now I can shuffle it and I can write Cp minus Cv can be taken there, and this comes this side, will be T times del V by del T, that is there at constant pressure, times the opposite, P by T P by T at constant volume. So this, my dear students, is equation number I. Equation number I. So this is your Cp minus Cv. Okay, Cp minus Cv. Understood? This is there. Got it? If you are not interested in this theory part, let me tell you, I'll give you the notes. Trust me. Okay, take the screenshot. I'll give you the notes. Okay. You'll simply study each and every step and you will be able to do it. Huh? I'll give you the notes. There is no worry. We'll finish even early than what we have predicted. Is it okay? I'll provide you the notes. Is that fine now? Is that fine now? Please tell me. I'm asking you. Up till here you have understood? Okay. After this I'll provide the notes. Will that be fine? I'll simply explain now Joule-Kelvin coefficient and your other Clausius-Clapeyron equations. Tell me, do you want notes? No. Now, this is there. Also, temperature is a function of pressure and volume. Temperature is a function of pressure and volume. No, you don't need to say sorry, yaar. You don't need to say sorry. See, when I'm giving this much, I expect at least the numbers in return, but you don't need to say sorry. Anyways, let's apply theorem number 3. Let's apply theorem number 3. So for theorem number 3, what did we have? Z, X, Y. Remember, del P by del V at constant T times del V by del T constant P times del T by del P at constant V minus 1. You remember this, no? So this P by T I can replace. Del P by del T at constant V can be written as minus. I put it there. This minus comes to this side. Right? Del V by del T times P by V at constant temperature. This is equation number EFGHIJ. Do you know, are you understanding what I have done? I have simply taken this term to that side. If I simply take this term to that side, it becomes P by T now. You understood? It becomes P by T now. Simple. Substitute from equation number J into equation number I. We need to simply do that. Okay? We need to simply do that. J into I. That result in place of this. Yeah. Do it, please. Understood? Okay. So see, in place of this, I need to replace that, which means that Cp minus Cv, a very beautiful equation will come out, will be T times del V by del T, that is already there, times, now I am substituting, minus del V by del T P by V, minus will come to this side, it will be squared, minus T times V by T squared P by V temperature, Cp minus Cv. Got it? This, my dear students, is your equation number 7th. Many a times it has been asked in civil services examination. Many a times it has been asked in your civil services examination. Okay? Many a times it has been asked in your civil services examination. But don't worry, in GATE examination, proof is not required. Only we'll see the conclusions. Only we'll see the conclusions. Please see. Conclusions. If we were studying for ESE, I would have taken this in much detail. But only conclusions are important here. T is absolute temperature in Kelvin, which is always positive, right? Absolute temperature is always positive. Number 2, see, whatever be the value inside, outside you have the squared, you have the square, that is always positive. Now, number 3, del P by del V, constant temperature. What is it? It is simply the slope of an isotherm or an isothermal process on the PV diagram. Is it not? Is it not? Yes, it is. PV diagram, isothermal, it is slope, P by V, dy by dx, dy by dx. Is it clear? Now, so this is always negative. We have already derived it. This one is always negative. Why? In isothermal, pressure decreases, volume increases, and pressure increases, then volume decreases. We have already studied PV equals to constant, right? That is there. Means it is negative. Therefore, Cp minus Cv is positive. Always. Means Cp minus Cv is greater than 0. Means Cp is greater than Cv. For any gas. For any gas. Be it ideal, be it real, any gas, we have Cp minus Cv greater than 0 or Cp greater than Cv. Is it clear, everybody? Is it clear, everybody? Fine. Now I am giving you some homework. Number 1. Prove Mayer's relation using equation number 7th. Number 2, prove that for solids and liquids, Cp equals Cv. ये दो homework, these two homeworks you need to do. Okay? So using this equation for an ideal gas, you need to prove Cp minus Cv is R, which is Mayer's equation. And for solids and liquids, that is incompressible, you need to prove that. Okay? Simple. Chalo, do this. Take the screenshot. No problem, Radhe bhaiya. No problem. And students have messaged 1 or 2 that sir, no, not 1 or 2, 5 or 6 actually, that sir, net is gone, and 1 or 2 are saying battery is gone. No problem, ठीक है. Fine. Shall we start now? Up till now we have done 7 equations. Okay. You remember isothermal compressibility? Huh? Isothermal compressibility, KT. What is KT? Compressibility at isothermal or at constant temperature. Yes or no? In fluid mechanics you study compressibility. What is compressibility? Compress होने की ability. Compress plus ability gives you the word compressibility. What's the meaning of compressibility? Ease with which a fluid can be compressed. Right? So this compressibility is simply inverse of bulk modulus. Why it is? You will study in fluid mechanics. Okay. So this formula in turn becomes minus 1 by V del V over del P at constant temperature. Why negative? Negative sign because as pressure increases, volume decreases. And this is equation number 8. I should tell you that you need to, you must have gone through this. Yes or no? You must know this. That's what I'm not taking it in much detail because you must be aware about it. In fluid mechanics it is told, fluid mechanics it is explained, and whenever you are going to study fluid mechanics, then see what is compressibility. Compress होने की ability, the ease with which any fluid can be compressed, ease of compression, compressibility. That is inverse of bulk modulus. Higher the bulk modulus, lower will be compressibility, and vice versa. So the formula is like this. Got it? For isothermal. Understood? Next. Coefficient of volume expansivity, beta. I'll tell you what it is. See what is beta? 1 over V del V by del T at constant P. Simple. Now I'll explain you what it is. Okay. Equation number 9th. Now what does it tell you? See, have you seen, Amit sir explained it, no? Okay, so there is no need to go, no need for me to go into the depth of it. You understand, right? You understand it, right? You understand it well enough that how we explain this. Okay, now let me tell you coefficient of volume expansivity. Let's talk about coefficient of volume expansivity. Beta equals 1 by V del V by del T at constant P. Let me tell you, my dear students, please let me tell you. Have you heard about hot air balloon? So what happens as we change the temperature, the volume changes, right? Volume increases, density decreases, the balloon rises up. In the same way, you have seen these ACs, air conditioners. These air conditioners are always, they are installed at higher elevations in the room. They are not installed in the lower part. Why? Because as temperature, see, since mass is constant and mass equals density volume, differentiate. When you are going to differentiate it, what are you going to get? 0 rho dV Vd rho, right? It becomes what? dV by V minus d rho by rho. Simple. Is it not? Yes or no? Minus d rho by rho. Finished. Now I can substitute means beta can also be written as minus 1 by rho del rho by del T at constant P. What am I trying to tell you? Why negative sign? Because beta is a property and can't be negative as temperature increases, density decreases. So this del rho will come out to be negative. To counter this negative term, we need to have a minus sign, and that is what have been done. Discussed? Does that mean? No, listen. I'm talking about all the ACs. Never even in window AC, you will see that it is installed near the legs. Got it? Never even in the window AC. Okay? Understood? So what happens? What happens? You can see for yourself. So as P is equal to rho RT, yes or no? At constant pressure, rho is inversely proportional to temperature. As temperature increases, density decreases. Means if dt is positive, temperature increases. D rho will be what? Negative. That's what it is explaining. Got it? This term, many people might ask you, what does this term explicitly explain? So the definition of this term is that it is the ratio of volumetric strain by per unit temperature change. Means how much volumetric strain is developed for a unit temperature change. Why is it important? Because it explains the phenomenon of hot air balloon, the phenomenon of refrigeration, the phenomenon of air conditioning. There are many terms to that. Okay? Understood? Is it clear? Is it clear, everybody? Say yes or no. Is it clear, everybody? Great. Now, what am I going to do? What am I supposed to do? From equation 8 and 9. If we talk about equation 8 and 9, see, kT times V equals minus del V by del P at constant T. But if I do this, del P by del V at constant T, it will be minus 1 by KTV. KTV, yeah, exactly. And this is equation, this must be EHIJK, equation number K. Also, beta V equals del V by del T at constant P. Now if I do the square by del T, beta squared V squared L. So substituting from equation L and K in equation 7. Now I am going to substitute in 7. Now I am going to substitute this in 7. Please take a screenshot. Please take a screenshot, my dear students. Then we'll proceed forward. Okay? I think you might have. Now what are you going to get? Cp minus Cv will be what? Minus T times beta squared V squared into minus 1 by KTV. Yes or no? Right? V will be cancelled out. Minus will be cancelled out. So what are you going to get? TV beta squared over KT. Equation number 10th. Right? Okay? Normally Cp minus, this is for real gases. For ideal gases, Cp minus Cv in general is R. But for real gases, it is not R, it is TV beta squared over KT. What is beta? Coefficient of volume expansivity. What is that? 1 by V del V by del T at constant P. What is KT? Isothermal compressibility. And what is that? Minus 1 by V. 14 times asked in UPSC civils, engineering services and civil services combined. Got it? Is it done? Understood? Understood, everybody? Understood, everybody? I hope it is clear. I really hope that it is clear. Shall we? Now, let's start. Clausius-Clapeyron equations. These are very important for GATE. Very, very, very important for GATE. Right? Clausius-Clapeyron equations are very important for GATE. Let me deal with this. After this, a last topic will be remaining. And also I'll tell you about compressibility factor a little bit. And then we'll call it a day. Okay? See. First of all, it gives the slope of a phase change process on PT diagram. Okay, let me tell you this now. Do you remember this? We drew this PT diagram somewhere. Yes. You remember this PT diagram? Now let us suppose that we are interested in finding the slope. Okay? I told you this is negative slope, this is positive slope, this is negative slope for water. But how much is the value? How would we find that? So for that, Clausius equation is given. Understood? Understood? Now from Maxwell's equation. Maxwell's equation. Now what does Maxwell equation tell us? How does it explain? So the Maxwell equation tells us that del P by del T will be C. तुम्हारे प्यारे Sir Varun, I still have not remembered them. S by V. Right? Is there any need for speed? I mean, is there any need for the negative sign? No. Not at all. Is it clear? Simple. For a phase change between, I told you already in thermodynamics we only study about, I told you already in thermodynamics we only study between, we only study about what? We only study about this, liquid and vapor. For a phase change between liquid to vapor, see del P by del T at constant V will be equal to Sg minus Sf. You remember? Vg minus Vf. Right? Okay. I can also write it as mass. I can take common Sg, specific entropy, over mass taken common Vg minus Vf. Is it clear, my dear students? There was a question based on this year. This mass will be cancelled out. This mass will be cancelled out because it will be taking place between G and F. So P by T equals to Sg minus Sf over Vg minus Vf. Logic is clear? All right. Now we know that Vg minus Vf, Sg minus Sf equals to Hg minus Hf over T saturation. Understood? Hg minus Hf upon T saturation. Is it there? Yes, it is there. It is there. We know this. We have done this. Which means that I can substitute del P by del T. Constant V will be written as what? Hg minus Hf over T saturation times Vg minus Vf. Understood, everybody? This is equation number 11, and this equation number 11 is known as Clausius equation. This is only known as Clausius equation. And Emile Clapeyron, a very prominent researcher of his time, he did some amends. He did some amends in this equation only and gave the equation in such a form. We'll see it. But meanwhile, please take the screenshot. So now, no. Let me give you more detail about it. So what does this Clausius equation tell you? It is the slope of phase change process, very specific liquid to vapor phase change process between on PT diagram. Okay, it is on PT diagram. Understood? Yeah, please take the screenshot. Please take the screenshot. Hope it is clear. Hope it is clear now. Okay. So there are some changes which you can think of yourself. Like for example, since small v is 1 by density, which means that for liquids, density of liquid is much greater than density of gas. Yes, liquid's density is much greater. 1 by liquid's density is much lower than 1 by gas density, which means that VL is much less than VG. Therefore, VF or VL, one and the same thing, can be neglected with respect to VG. VG means that del P by del T at constant V equals to what? Latent heat, yes or no, upon T saturation into Vg. This is also a form. Now, Emile Clapeyron thought, oh God, I'm sorry, just a minute, हालत खराब है भाई. Emile Clapeyron, he thought that ideal gas equation can be applied right from saturated vapor line. ठीक है, saturated vapor line से it can be applied directly from the saturated vapor line. Say yes or no? Say yes or no? It can be applied directly from saturated vapor line. Is it clear? See, like this. This is G, let us say. So we can apply from there. So PVG equals to R saturation temperature. Corresponding to this, we'll have saturation temperature only. Means Vg can be written as R, oh God, T saturation by P. Therefore, upon substitution, what are you going to get? You are going to get del P by del T, constant V equals to LH, latent heat, over T saturation, RT saturation over P. P will go up. Equation now becomes del P over del T, constant V, PLH over RT, saturation 2. Equation number 12. This is Clausius, because it is derived from Clausius. It was given by Clapeyron equation. Okay. Now remember the trick. याद करने का तरीका. Let me give you the trick to do it. So what is the trick to do it? The trick to do it is very simple. The trick to do it is very simple. How to do this? See, del P by del T, it gives you slope on PT, means del P by del T at V equals PLH upon RT saturation squared. यही है ना? P stands for polio, PL, right? Polio. H stands for hospital, right? RT stands for Aarti. Aarti. SAT stands for Saturday को. This 2 stands for 2 बार गई. पोलियो हॉस्पिटल आरती सैटरडे को 2 बार गई, राइट? आरती सैटरडे को 2 बार पोलियो हॉस्पिटल गई. Whatever. Understood? Understood everyone? Understood everyone? Okay? Yeah. So wait a minute. Let me tell you. Take the screenshot first. Take the screenshot first. Take the screenshot first. Okay. Okay. So now, I'm having severe problem, throat problem, speaking, and the fever is rising again. So, I hope you all have understood. Only one topic is remaining. Joule-Kelvin effect. Okay? That Joule-Kelvin effect, either I will provide the recording on tomorrow. Okay? Either I'll provide the recording tomorrow, or we'll do it in a live mode. Only half an hour or 1 hour something is remaining. Okay? But because I'm not able to speak now, I'll call it a day. Will that be fine? Tell me, because I'm really not feeling well. This travel and cold water here and there is, and also season changing, causing a lot of trouble for me. Anyone, please don't be upset. Don't be upset. Yeah, unsteady flow is there, no? Unsteady flow. Unsteady flow is not done, I guess, up till now. But in steady flow, right in the beginning, there is a small change. If we are able to do that, you will be able to solve the questions. Okay, I'll provide that in recording as well. Okay, I'll provide that in the recording as well. Okay, so please, I apologize for this, but I never wanted to cancel the class in the beginning itself. I was not feeling well, but I took it anyways. Thank you so very much. Love you guys. Please do take good care of yourselves and prepare for your Menti, which is on Tuesday. And from Wednesday, we are starting heat transfer. Okay? And heat transfer, Wednesday. Okay? Yeah, there's a problem. Okay, guys. Thank you so much. Love you all. Thank you. Menti is on Tuesday. The whole syllabus is coming. And attempt the questions. They are very important. Thank you. Bye-bye. Thank you. Thank you. Love you all. Love you, my younger brothers and sisters. All of you. Sumit, you also take rest. Take medicine. Take rest. Thank you.